Hello and welcome to the Complete SQL course with MySQL Database Learn by Doing, the only course you need to learn and master SQL. I'm Daniel Tate and I've been working with SQL and relational databases Hello and welcome back. In this video, we are going to go through how to install MySQL on Windows. We will then open up MySQL Workbench and run a file which will create some databases which we will use throughout the course. Okay, so the first thing is to check this video for a resource link that contains the course databases SQL file. This SQL file will be used to create the databases used in the course. So on this video, you'll see the resource button, which looks a bit like this, and just click on it and it brings up this file, course databases, MySQL. So just click on that file name to download it, and you do not need to open this file. Just remember its download location. For most people, this will be the downloads folder. Okay, once you have done that, then open up a web browser. Okay, so I've got my web browser open, and in Google, I'm just going to search for MySQL. And the one I want is this one here for mysql.com. So click on that. And you want to go up here to the downloads page, and so just click on downloads and scroll to the bottom here, and where it says MySQL community downloads. So we're going to download a community edition of MySQL, and it's absolutely free to use. So click here. And the one we want is MySQL installer for Windows. So click on this one here. So we have two installers shown here, and the first one is MySQL Installer Web Community. So this installer requires an online connection while running the installer. The second installer is for installing it offline. So I'm going to have an online connection while installing it, so I'm going to download the first one here. So on this page, it's just asking if we want to log into an Oracle account or sign up for one. I'm just going to click on No Thanks, Start My Download, and that's because you do not need an Oracle account to follow this course. So click on No Thanks, and so now it's installing the file, and I'm just going to right click here and go Show in Folder. So as you can see, it has downloaded the installer file. So now what I'm going to do is just double click on this file. Okay, so I'm going to click on Yes. Yes again. So here we choose the setup type, and I'm just going to leave it on the default for developer default. So click on Next. So now it's giving me a list of products that will be downloaded in this installer. However, before this step, you may get a message saying that some extra components are needed. So just go through and install those first, and then click on Next, and then you should get to this page here. So the first product is MySQL Server. So that's the actual server itself. And the second one, MySQL Workbench, this is the graphical user interface tool that we'll be using throughout the course. And basically it's a convenient tool where we can write our SQL queries and manage our databases. And we've got a bunch of other products, and it also comes with its own samples and examples. So we'll leave all of these on, and we'll just click on Execute to install them. Okay, so as you can see, I'm getting some errors here. So I'm just going to click on this Try Again for each of them. And we just keep going through the ones which say error and click on Try Again. Okay, so that looks like it's downloaded all of them now. So now I'm just going to go Next. And so we have ready to install for all the products. Click on Execute. This might take a few minutes to install, so I'm going to pause the video and come back when it's finished. Okay, so that's now all installed. So we just go Next. And then Next again. And Next once more. Okay, so now we're going to set up a password, so click on Next. Okay, so now we're going to set up a password for the root account. So I'm just going to use the password, so I'm just going to write password, repeat the password. So if you choose something different, just remember to write it down somewhere, and we'll need this password later on to connect to the server instance. If you lose the password, I'm sorry, I won't be able to help you with that. You'll need to do the install again. And also down here, we can set up a user account. This is not necessary for the course, so I'm just going to click on Next. And then we just leave it on all the defaults here and click on Next, and then click on Execute to apply the configuration. Alright, and then click on Finish. Next. So just leave it on the defaults, clicking on Finish. Click on Next. Alright, so here is where we're going to connect to the server. So you need to put in that password that you set in a previous step. So mine was password, so I'll just write password, click on check. Alright, so we've got connection succeeded, so that worked. Click on Next, click on Execute, and click on Finish. Next. Okay, so we've got installation complete. Click on Finish. So this MySQL shell is a command prompt we can use to give instructions to the database instance. We don't actually need it, so we'll just close that. Okay, so this is MySQL Workbench, and this is the tool we'll be using throughout the course. And as it says here, it's the official graphical user interface for MySQL, and it allows us to design and browse database schemas, and we can also do things like run SQL queries. And that's what we'll be doing throughout the course. So by default, it should come up with a connection called local instance, and this is the one we created during the setup. If it doesn't come up with this, just click on the plus button here and do a new one by typing local instance, and then click on store in vault and then enter in the password that you used during the setup. Click on OK and then OK again to create that new connection. I don't need to do it in my case because it has come up with it already, so I'm just going to go cancel. To open the connection, we're just going to click on it, enter in the password, and you can save the password in Vault if you want. I'm just going to click on OK. Okay, so here is MySQL Workbench, and we've got a few things here. So we've got our SQL editor window here, and this is where we can write our SQL. And then over here we've got the navigator window, and this is where we can see the different databases. So in MySQL terminology, a database is the same as a schema. So it says here schemas, so we have our database schemas. So we've got one called Secular, one called Sys, and one called World. And we can expand this, so let's say we expand the World database, and then we've got the different objects within that database, such as tables, views, stored procedures, and functions. So let's click on tables, and the World database has a few tables in it, one called city, one called country, one called country language. So if we expand the city table, okay, and then we've got columns, indexes, so we've expanded columns. So the city table has some columns, ID, name, country code, so we click on name. Down here it will give us some information about this column. So now what we're going to do is open up that course databases SQL file that we downloaded earlier to our downloads folder, and we're going to run that file, create the databases that we'll use during this course. So come up here and click on this little folder icon which says open a script file in the editor. Then navigate to where you downloaded the file to. So for my case it was the downloads folder, and I'm going to select the file. Okay, so I'm going to just click at the start of the file, and then I'm just going to go up to here where they've got this lightning bolt symbol, and this lightning bolt symbol is to execute the script. So I'm going to click that one time. So click that one time, and down here in the output window, so I'm just going to make this a bit bigger, we can see all the statements that it's running. So it's at the moment it's inserting data into the tables. So just leave that running for a while until it looks like it's completely stopped. So it's done 3976 SQL statements. So after the script is completely finished running, you can then close this editor window here. So just close it, clicking on X. Okay, let's now just check that those database schemas have installed. So we're going to go across the schemas here, and we can either click this little refresh button, or we can right click on the white space and go refresh all. And so do that, and you should see some new schemas come up. One called OES, one called HCM, and one called Bird. Okay, so that's it for the Windows installation tutorial. So you can go ahead and close down this application by going to File, Exit. Welcome back everyone. In this video, I'll be giving an overview of the course challenges. And firstly, from my own experience, I've done courses before where I just followed along with the instructor and there were no exercise challenges. And what I found was I quickly forgot what I had learned. And for that reason, I've included lots of challenges in this course. Alright, so throughout this course, you'll receive sets of challenges. And these challenges will help to reinforce your learnings in SQL by actually writing SQL. Some of these challenges cover material from multiple lectures, so at times you may find it useful to go back and revisit some of the lectures. Challenges mostly involve querying data from one or more of the course database schemas. However, in some challenges, you'll be creating new data structures, such as tables, stored procedures, and views. In addition to the challenge lectures, a PDF file of each set of challenges is provided as a resource. There'll be two versions of each PDF file, one with hints for each challenge, and one without any hints. So if you want to have a go at doing some challenges without having a look at the hints, that option is available to you. But just note that the video lectures include the challenge hints. Some lectures have one quick challenge where the solution is given in the same lecture. So it is just one quick challenge and then I will give you a prompt to pause the video and for you to give the challenge a go. And then straight after that we will go through the solution together. And in this course, the solution to every challenge will be given. So after each set of challenges, we will walk through the solution to each challenge. This is where we go through and describe the solution in detail. You can also download the solutions as .SQL files, and these are given as resources throughout the course. Occasionally, multiple ways of solving a challenge are given. So in SQL, often there are multiple correct ways to write a query and get to the solution. In some of these cases, I'll provide an alternative way of writing a particular query and arriving at the correct result. And finally, just note that SQL is a declarative language. So this means that we specify the instructions of what we want the SQL engine to do. However, we do not tell the SQL engine how to do it. How the SQL engine decides to execute a query is what is called the query plan. The query plan affects the efficiency of queries, and this extends into the vast topic of query tuning. However, the main focus of this course is on increasing your knowledge and know-how of the SQL language, rather than so much on query optimization. With all that being said, I really hope you do give the challenges a go, as they will help test your understanding of SQL, as well as solidify your SQL skills. Okay, so that's it for the overview. See you in the next lecture. Hello everyone. In this lecture, I'll be giving a brief overview of some popular relational database management systems on the market today. However, before going through that, let's go over some pronunciation. So there are two ways to say SQL. We can either say the letters, as in SQL, or we can say the word SQL. Either way of saying it is fine. Personally, I tend to say SQL most of the time. However, it does matter when saying the name of various database vendors. For example, MySQL is pronounced as MySQL, whereas Microsoft SQL Server is pronounced as SQL Server. Sometimes I trip up and accidentally use the wrong pronunciation, but if you want to sound professional at your next job interview, then make sure you check that you're using the correct pronunciation for the database software name. Okay, with that aside, let's go through some commonly used database vendors. So in this course, we will be using a database called MySQL. And fun fact is that MySQL is named after the co-creator's daughter, My. MySQL is an extremely popular database. In fact, in the 2021 Stack Overflow Developer Survey of over 70,000 developers, MySQL was the most widely used database amongst developers, with about half the survey respondents indicating that they had extensively used MySQL database within the past year. There are many reasons why MySQL is so popular. One is that it's open source. This simply means that anyone can install and use the basic software, while also enabling third parties to modify and customize the source code. However, more advanced versions of MySQL Database, which offer additional capacity and services, come with tiered pricing plans. But in this course, we will be using the free version of MySQL. MySQL is also popular because it is fast, reliable, and scalable, and it has many security features to keep your data secure. Now, each database has its own dialect, i.e. version of the SQL language, for interacting and querying the database. And there's an institute called the American National Standards Institute, which is abbreviated to ANSI, and they publish documents that outline what the syntax for standard SQL should look like. One way to think about this is like an English university publishing a grammar book defining the grammar rules for the English language. So each database vendor, such as MySQL, chooses the degree to which they follow the standard. In the MySQL documentation, they mention that they try to follow the ANSI SQL standard, but that MySQL server performs operations differently in some cases. Okay, so another popular open source database is called PostgreSQL. PostgreSQL is another great database that has been gaining in popularity over recent years. However, because PostgreSQL is not as widely used as MySQL, there's currently a smaller number of third-party tools available for developers. PostgreSQL claims high but not complete conformance with the latest SQL standard. Another database vendor you might have heard of is Oracle. So Oracle Database is an exceptional database that is widely used in the corporate world. But unlike MySQL or PostgreSQL, Oracle is not open source. And I should mention that Oracle owns MySQL. So Oracle bought MySQL from a company called Sun Microsystems back in 2010 for $7.4 billion. At the time, there was concern about what Oracle planned to do with MySQL. However, to date, Oracle have kept MySQL as a successful open source project, and this has allowed new features to continue to be added to MySQL database from open source contributors. Like Oracle, another paid-for database system is SQL Server. SQL Server is a Microsoft product, and it's another great database which has lots of features. SQL Server is known to be relatively easy to install and configure. SQL Server is also widely used in the business world and integrates well with other Microsoft products such as Power BI. I actually have another SQL course similar to this one, except that it uses the free developer edition of SQL Server. So if you're interested in SQL Server, check out the link to that course in the resource attached to this lecture. Okay, so even though SQL Server is a paid product, it does come with a free edition where you get your own development environment and you can explore all the features and functionalities of the latest SQL Server version. And Oracle Database offers a similar thing, so Oracle Database also has a free Express edition for developers. Okay, so the last database I want to mention here is SQLite. SQLite, as the name suggests, is a lightweight database that is used by millions of applications with billions of deployments worldwide. In fact, SQLite is the most widely deployed database engine in the world today. Google uses SQLite in their Android smartphone operating systems, and Apple also uses SQLite in many of the native applications running on macOS desktops and on iOS devices such as iPhones and iPods. Unlike most other SQL databases, SQLite does not have a separate server process. SQLite is pretty cool as it does provide a full-featured SQL implementation. You can write queries to join and group data, and you can even set up constraints and indexes just like in any other relational database. You don't even need to install SQLite. You just download the SQLite libraries, and then it's ready for creating the database. However, SQLite is used for specific purposes, and it's used to handle low to medium traffic HTTP requests, and it also has a relatively small database size. Okay, so a common question is, which dialect of SQL should I learn? In my opinion, it really doesn't matter too much which one you start off with. Once you learn one of them, it is relatively easy to pick up another. I once had a work colleague who was keen to learn SQL. However, at the time, the organization was planning to migrate from Oracle to SQL Server. Therefore, my colleague reasoned that there was no point trying to learn Oracle and that he would wait until SQL Server was available. However, it wasn't until a year later that the database migration actually happened. And when the organization did shift to SQL Server, I found that I was able to transfer about 80% of my SQL skills, and the other 20% was pretty easy to pick up because I was already familiar with SQL from working with Oracle. Now, each relational database does have its own quirks and functions, but overall, their SQL dialects have a lot in common, primarily because they want to at least partially comply with the ANSI SQL standard. Okay, that's it for now. See you next time. Hello everyone, and welcome to this lecture on understanding the foundations of SQL. Let's get started. SQL, which can also be pronounced as SQL, stands for Structured Query Language, and it is a language for querying and manipulating data stored in relational databases. SQL has a strong mathematical foundation, and this strong foundation is one of the reasons why the SQL language continues to be relevant in the marketplace today. Luckily, you don't need to be a mathematician in order to know how to write good SQL. All you need to know are some key principles, and you will have a much better understanding of the language. SQL is based on the relational model, which in turn is based on set theory and predicate logic, and we will discuss those in just a moment. But first, I'll just mention that the relational model is a mathematical model for data management and manipulation. It was first created by Ted Codd in 1969 and is the cornerstone of SQL and relational databases. Even though the SQL language is based on the relational model, it deviates from the model in a few ways, which we will see soon. Alright, so a relation in the relational model is what SQL attempts to represent with a table. Let's now take a look at an example of a relation. So here we have a relation which has a set of employees, and a relation has a heading and a body. The heading is a set of attributes which SQL represents with columns, with each attribute given a type. The body is a set of tuples which SQL attempts to represent using rows. So in this relation, we have the headings, which are the attribute names, and attribute names are also called column names. It is important to note that the attribute names are by themselves, not a row. Okay, so in this relation, we have 4 attribute names, which are employee ID, first name, last name, and salary. In SQL, all attribute names need to be unique. Also, in the relational model, each attribute has values that are of a certain type. So what do we mean by type? Well, the values of each column should be the same type of thing. For example, if we look at the employee ID column, each value in this column should only contain the number used to uniquely identify each employee. For instance, it should not contain any other attribute of an employee, such as their phone number or email address. And the same is true of the other columns. First name should only contain the first name of each employee, last name should only contain last names, and salary should only contain the salary of each respective employee. Therefore, in this case, the values within each column are of the same type. Let's now take a closer look at the body of this set. So in this relation, we have a set of 4 tuples, i.e. rows. So let's take a look at the tuple for employee ID 1, which is Verihill. Then we have another tuple, which is for employee ID 2, which is Ben Jones. Then we have Herb, and then Chelsea. Okay, let's take a look at all of them again. SQL attempts to represent tuples as rows in a table, and sometimes people use those terms interchangeably. Okay, so one of the important principles of a set is that a set has no duplicates. A duplicate row is one which will have all the same values as another row. So currently in this table we have a set of tuples as there are no duplicates. So what would a duplicate look like? Let's just add one in to demonstrate. Now this table has a duplicate row with all the same values entered for Chelsea Walsh on an additional row. So we can see that these two rows here have the exact same values, and therefore we have a duplicate row. So in SQL, there is nothing stopping us from inserting a duplicate row into a table, unless we have added a thing called a primary key constraint to a column in a table. We will be covering primary keys later on in the course, but for now, I'll just mention that a primary key is a type of constraint we can add to a table, and essentially it makes sure that no duplicate values can be inserted into the column with the primary key applied to it. Therefore, a primary key effectively prevents duplicate rows because we would have at least one column which was guaranteed to have unique values. So in this table, typically we would put a primary key constraint on the employee ID column, and this would mean that the values for the employee ID column must always be unique. Therefore, we would get an error message if we tried to insert duplicate values into the employee ID column. So in this case, if we had a primary key on the employee ID column, we would not be allowed to insert the value of 4 multiple times into the employee ID column, as we have here for Chelsea Walsh. Okay, let's now remove the duplicate row. Another important principle of sets is that we should consider each set as a whole. This means that we aim to work with the whole set, rather than interacting with the individual elements of the set. Now, if you come from a procedural programming background, this will involve a bit of a change in mindset. In programming, the natural way of working with data is with iterations. Iteration is a process where a set of instructions are repeated a specified number of times or until a condition is met. However, in SQL, the best and fastest way to write queries is to interact with the table as a whole. Where possible, you should try and avoid using iterative constructs, such as loops that iterate through one row at a time. From the perspective of the relational model, the best way to work with relational data is to use relational operations that work with whole tables at a time. The next important principle of working with sets is that there is no relevance to the order of elements in a set. For example, we could specify a different order of the tuples, and this would still be considered the same set. Likewise, we could also change the order of the attributes, and it would still be considered the same. The relational model is also based on predicate logic. A predicate is basically just a condition expression that evaluates to either true or false. For example, in this table, we might ask the following. Which employees have a salary greater than $85,000? And just by looking at the table, we can see that Ben and Vera both have salaries that are greater than $85,000. Therefore, the predicate condition is salary greater than $85,000 evaluates to true for both Ben and Vera, whereas this predicate evaluates to false for both Chelsea and Herb, as they have a salary that is not greater than $85,000. In this case, Chelsea and Herb have a salary which is exactly equal to $85,000. Predicates are used throughout the relational model, and predicates can be used to filter data as well as enforce data integrity. Okay, so that's it for the foundations of the SQL language, and occasionally we'll be revisiting these principles of the relational model throughout the course. Okay, welcome to the select statement lecture. The select statement is the most commonly used statement in SQL, and it is used to retrieve data from a table. We are going to start off doing some basic select statements, but as we progress through the course, we will be doing some more complex select statements. For example, ones that involve joins, subqueries, set operators, etc. Okay, let's go through the basics of the select statement. So here we have a table of employees, and let's say we just wanted to select the employee ID column. We can do that by writing the following query. So first we type the word select, and then we type the name of the columns we want to select. In this case, we just have the employee underscore ID column. Then we type the keyword from, and this is where we let SQL know which table we want to get the data from. In this case, it is from a table called employees. And at the end of every SQL statement, we have this semicolon. So that indicates the end of the statement. In this statement, the first line is what we call the select clause, and the second line is the from clause. Alright, so there are a couple of things to note, and one of them is that I have capitalized the select keyword and the from keyword. However, you don't need to do this. Instead, if you want to, you could write these SQL keywords in lower or mixed case if you want to. However, I find SQL code easier to read if the keywords are in uppercase. Also notice that the from keyword has been put on a new line. This is not mandatory to do, and you could instead have it all on one line, for instance. So we could have select employee ID from employees all on one line, and this will work just fine. However, once you start writing much longer and more complex SQL statements, putting the different clauses on new lines makes the code a lot easier to read. Okay, so let's go back to how it was before. So if we want to select multiple columns from a table, then we just write each column name separated by a comma. So let's say we wanted to select both the employee ID and the last name columns. So now we have select employee ID, then we do a comma, and then we write the name of the next column we want to select, which in this case is the last name column, and then we have from employees. And notice that the last column we specify in the select clause, so in this case it's the last name column, does not have a comma after it. So we only have commas between columns that we want to select in the select clause. Also, we can change the order of the columns returned by the query. For instance, we could specify the last name column first. So now we have specified select last name comma employee ID. So now in the query result, we get the last name column specified first. And note that the select statement does not change the order of the columns in the underlying table. The select statement by itself does not change the underlying table in any way, shape, or form. Okay, so let's select all columns from the table. Now in the select clause, we are selecting all the columns from the underlying table employees. A quick way to select all columns from a table is to use select asterisk. Select asterisk, or as I like to say, select star, is a quick way to select all columns from a table. If you are writing queries, it is okay to use select star to select all columns. However, when it comes to creating a view or inserting data into a table, then it is considered bad practice to use select star. Later on we'll be taking a closer look as to why that is. Okay, let's go back to writing the column names in full. Now we have each column name, and in this example each column name is on a new line, and the column names have been indented. This is not necessary to do, but I find indented code easier to read, particularly if it is a complex SQL statement. Let's now exclude the salary column from the query result. Something that we can do in SQL is that we can alias object names. So we can alias things such as column names and table names if we want to. An alias is where we temporarily rename something, but only within the context of the query. For example, let's rename, i.e. alias, the column first name to emp first name. So now we have first name, then we have the keyword as, and then we specify what we want to alias the column to. So we have the alias emp first name. The column names remain unchanged in the underlying employees table. All we have done is we have temporarily renamed the first name column to emp first name in the query result. So it's only been renamed within the context of this query here. And note that this as keyword is optional. For instance, we could have excluded it and we would have still got the same result. So even though the as keyword is optional when aliasing columns, it is good practice to get in the habit of using it as it makes the code more readable. This form shown here is less readable and it makes it a bit more difficult to spot a bug involving a missing comma, for example. So here we have accidentally forgotten a comma between the first name and the last name columns. However, the query still works, and what happens is we get the first name column getting renamed to last name in the query result. So these are the actual employees' first names, but we've accidentally renamed it to last name. So this is clearly not the result we wanted. And instead, if we always use the as keyword when aliasing columns, then it's a lot easier to spot this type of bug. Okay, so let's go back to select all columns again. So far we have been selecting columns from a table. Something else we could do is to create our own virtual columns within the query. For example, let's say we wanted to add on a column called bonus, and we want the bonus column set to a value of $4,000. Let's have a look at how we can do that. So all we needed to do was include an expression in our select clause, which was 4,000 as bonus. And this gets added on as a column in the query result. So we have this bonus column here, all with 4,000 for each row. So this only exists within the query result. No column has been added to the employees table. And this is what we call an expression. Let's do another expression, and this time we will call it total, and we will set total equal to each employee's salary plus 4,000 for the bonus. So now we have another expression called total, which is salary plus 4,000. Something important to understand is that if we had instead tried to write salary plus bonus, for example on the right here, then we would have gotten an error message. And this is because conceptually everything in the select clause gets processed at the same time in an all or once manner. This is different to many other programming languages where expressions typically get evaluated from left to right. Therefore, we cannot reference the bonus attribute when we are calculating the total attribute because SQL conceptually creates both at the same time. We say that it does this conceptually because SQL does not physically process all expressions at the same point in time, but it has to produce a result as if it did behave this way. So I know this is a little bit to get your head around, but basically all it means is that we can't reference something else we've created within the select statement for a second expression. So in this case we're trying to reference the bonus column, but we also created the bonus column at the same time in the select clause. Now it doesn't quite look like that because we specified bonus first, but SQL treats it this way. It treats all expressions in the select clause as being created at the same time. Okay, so that's it for the introduction to the select statement. Hope you found that useful, and I'll see you in the next lecture. Welcome back. In this lecture, you will have a few challenges which involve writing simple select statements. Hints will be given for each challenge. In the first challenge, you are to use a select statement to get the first name and last name of all employees. Let's take a look at the hints. So the first hint is that you'll be querying the table called hcm.employees. So HCM is the database name and employees is the table name. Remember to write a semicolon at the end of every query. So all queries should end in the semicolon. Place the cursor either at the end of the query or anywhere within the query and click on the execute button to run the SQL query. So the execute button is the lightning bolt symbol with the letter I on it, and it looks like this here. Okay, let's go through the second challenge. So for this challenge, you are to use a select statement to get the last name and city of all customers, and alias the last name column to customer last name in the query. So recall that an alias is temporarily renaming that column, but only within the context of the query. Alright, so the hints for this one are query the table called oes.customers and use the as keyword to alias the last name column to customer last name. Alright, let's take a look at the third challenge. So for the third challenge, use a select statement to select all columns from the oes.orderItems table. The hint for this challenge is use the asterisk in the select clause. So in the solution, we will discuss the pros and cons for this approach for selecting all columns in a table. Okay, so give those few challenges a go, and in the next video, we will be going through the solutions. Okay, welcome back. In this tutorial, we're going to go through the solutions to the select challenges. So I've just opened up MySQL Workbench, and I'm presented here with the home screen. So I'm just going to click on where it says local instance to connect to the instance. So my password was the very top secret password. And this time I'm just going to click on this box here for save password in Vault. And what that's going to do is it's going to save the password, and therefore next time I open up MySQL Workbench, I won't need to put in the password when I connect to the local instance. Alright, so I'll click on OK. And so here I can see my databases, and hopefully you've installed the course databases, so you should see Bird HCM OES. And here I've got a blank SQL editor. So this is where we can write our SQL. So I've already written the SQL, so I'm just going to open up that SQL file. So I'm going to click on the folder button here, and I'll open up the solutions to the select challenges. Before we carry on, I should mention that I've increased the size of the font here, and that's because my eyesight isn't the best. And if you want to do the same, what you can do is go to the edit menu here, go to preferences, and then click on fonts and colors, and you can increase the text size. So I've increased the text size of the SQL editor, which is this window here, to size 18, and for the result grid I've made it 14. And just note that you'd need to actually restart MySQL Workbench to see these changes. Alright, so just click on OK there. So the first challenge was to select the first name and last name columns from the HCM.employees table. So to write this query, we write the keyword select, we have a space, we write the name of the first column we want to select, which is first name. So first underscore name in this case. Then we have a comma, and after the comma we specify the next column, which is last name. No comma after the last column, and then we go straight to the from clause. So we have the from keyword. Then we specify the database or schema. Remember that in MySQL, a schema is the same as a database. So we have HCM dot, and then we've got the table name, and we end all our select statements with a semicolon. And if we look at the table in the navigator, so under our schemas we want to go to HCM, it's a table, and the employees table, click on columns, and so here we can see the two columns that we're selecting, first name, last name. Okay, so click anywhere within the select statement or at the end of it, and then click on this lightning bolt with the cursor on it. And if I hover over this, it actually tells me that it executes the statement under the keyboard cursor. So we'll click on that. Okay, so in the result grid, we get all the employees' first name and last name returned, and we can scroll down, and so we see all the employees. And down in the output, it gives us some more information. So we have a tick box to let us know the query completed successfully. We have the actual query, the time it was run, how many rows got returned. So we can see we've got 107 rows in the employees table. And also how long the query took to run. So it's very fast at 0.016 seconds. And note that in MySQL Workbench, by default, it only shows us 1,000 rows. So in this case, it doesn't really matter because the employees table only has 107 rows in it. But let's say we had a table with millions of rows in it. By default, MySQL will just show us the first 1,000 rows. And it does this because if we have a very large table, it might take quite a long time to load. However, in this course, all our tables are fairly small. We're in the thousands of rows, not the millions. So what we can do to change the default behavior is we can go up to here where it says limit to 1,000 rows and just use the drop down and select don't limit. So now when we run our queries, it's going to show all the rows in the table, no matter how large the table is. And one other thing I should mention is that I've put the from clause on a new line, and I've done this because it helps with the readability, but it wasn't strictly necessary to do. So for example, I could have put it up here and the query would have still worked okay. But general convention is to put the different clauses on new lines, and it really helps with readability. Okay, so moving to the second challenge. So for this challenge, we were to select the last name, but we were to give it the alias customer last name, and then we were also to select the city column from the oes.customers table. So we write select last name as, and then we give what we want to alias the column to. So we've got customer underscore last underscore name. So you can think of this alias as a temporary name that only exists within the context of the query. So we're not changing the last name in the underlying table in any way, shape or form, but just within the context of this query, we're giving it a new name. Okay, so let's click in the query, click on the execute I button, and there we have it. So we have customer last name and the city. So for the third challenge, we were to select all columns from the oes.orderItems table. And to do that, we simply write select asterisk from oes.orderItems. So we'll just click anywhere in the query, execute it. So now we can see all columns and all rows in the order items table. One thing to mention about select asterisk, or as I like to say, select star, is that sometimes it's bad practice to actually use this in our queries. And the reason for this is that the purpose of the query becomes less obvious. For example, we might have a select statement that is supplying some columns to an application, and if we write select star, then it's not clear which columns the application is using. Is it using all the columns, or is it using just a subset of the columns? So as a general rule, for this you want to be explicit and write out the columns. However, in saying that, I often use select star to get an idea of what's in a table. So often for our general purpose querying, it's fine to use. Alright, that's it for the lecture. Hope you found that informative, and I'll see you in the next one. Hello everyone, and welcome to the Select Distinct lecture. Let's get started. The select distinct clause is used to remove duplicates from the result of a select statement. Let's take a look at the syntax. Okay, so we just write the keywords select distinct, followed by one or more columns, and as usual, we separate each column with a comma. And then we have our from clause, so we have from the table that we are selecting from. Okay, so let's go through some important details to be aware of when using select distinct. Firstly, when only one column is provided in the select distinct clause, the query will return the unique values in that column. Whereas, when multiple columns are provided in the select distinct clause, the query will return unique combinations of values for the specified columns. And also, nulls are treated as a distinct value by the select clause. And we haven't actually covered nulls yet, but later on in the course, we'll be taking a close look at nulls and how we can handle them in our queries. For now, I'll just mention that a null indicates the absence of data. So if we have a cell with a null in it, then we can think of this as something which is unknown. Okay, with that aside, let's go through some examples using select distinct. So here we are selecting a few columns from a table called hotel rooms. Alright, so let's just select the room style column. Now, according to the relational model, an operation against a relation ideally should return a relation. In this case, it would be a set of unique values for room style. However, as you can see here, SQL does not remove duplicates by default. We can see that we have the value single on multiple rows, and we also have double on a couple of rows. So even though SQL does not remove duplicates by default, we can remove them using the distinct keyword. Let's have a look at that. So now the SQL statement is select distinct room style from hotel rooms. And we can see that currently this hotel has rooms which have a room style of either double or single. By using the distinct keyword in our select statement, we have removed the duplicates from the query result, and therefore we have returned a relational result. This is because we now have unique values in our query result. We can also use select distinct with multiple columns in order to get unique combinations of columns. Let's go through that. Okay, so now we are back to the original query, where we are selecting a few columns from the table. This time, let's just look at the room style and window view columns. Okay, so this query here has not returned a relational result because we have duplicate rows. And recall that a duplicate row is one where the values are the same as they are for at least one other row. For example, the values of single and ocean are duplicated on more than one row. So again, we can use the distinct clause to remove duplicate rows. So our new query is select distinct room style, window view from hotel rooms. And this is a relational result as we get a set returned. Recall that a set has unique combinations of values for each row. And notice now that we only have one row for the combination of values of single and ocean. So we have removed the duplicates, and we only keep one of each combination of values. One important thing to understand is that when we specify multiple columns in a select distinct clause, then we can still get duplicates within just one column. For example, with this select distinct query here, if we just look at the window view column, we can see we have a couple of instances of the value ocean, and we've got a couple of instances of the value mountain. Therefore, the window view column by itself is not unique in this query result. It is only when we combine window view with room style that we get uniqueness across both columns. In other words, the value of ocean by itself is not unique, but the combination of values double and ocean is unique. And the same is true for the other rows in this query result. Okay, so in summary, we've got a unique combination of values for both the room style and window view columns, as we specified both these columns in a select distinct clause. Understanding this concept of uniqueness that holds across combinations of values is really important when it comes to writing accurate SQL, and we will be revisiting this in later lectures when it comes to grouping data. Okay, that's it for now. See you next time. Welcome back. In this lecture, you will have a few challenges which involve writing simple select statements. Hints will be given for each challenge. In the first challenge, you are to use a select statement to get the first name and last name of all employees. Let's take a look at the hints. So the first hint is that you'll be querying the table called hcm.employees. So HCM is the database name and employees is the table name. Remember to write a semicolon at the end of every query. So all queries should end in the semicolon. Place the cursor either at the end of the query or anywhere within the query and click on the execute button to run the SQL query. So the execute button is the lightning bolt symbol with the letter I on it, and it looks like this here. Okay, let's go through the second challenge. So for this challenge, you are to use a select statement to get the last name and city of all customers, and alias the last name column to customer last name in the query. So recall that an alias is temporarily renaming that column, but only within the context of the query. Alright, so the hints for this one are query the table called OES.customers and use the as keyword to alias the last name column to customer last name. Alright, let's take a look at the third challenge. So for the third challenge, use a select statement to select all columns from the OES.orderItems table. The hint for this challenge is use the asterisk in the select clause. So in the solution, we will discuss the pros and cons for this approach for selecting all columns in a table. Okay, so give those few challenges a go, and in the next video, we will be going through the solutions. Alright, welcome back. So now we're going to go through the solutions to the select distinct challenges. And before going through the solution to the first challenge, I'm just going to select all data from the bird.antarctic species populations table just to get an idea of what's in this table. So I'll click in the query, click the execute button. Okay, so this table has 18 rows of data, and essentially it gives us the population count at various localities for various species. So for example, on the 12th of May 2018, a population count for species ID 1 was completed at Anvers Island, and we had a total population count of 91,000 on this date. And then later on September the 18th, another population count was done on this same island for the same species, and this time we had a population count of 90,000. Okay, so the first challenge was to select distinct values that occur in the locality column. So all we need to write is select distinct, then locality from bird.antarctic populations. So let's click in there, let's execute it. So this query gives us all the unique values in the locality column. So we have 4 different localities. Okay, let's move to the second challenge. So in the second challenge, you were to use a select distinct statement to get the distinct combinations for both the locality and species ID columns. So again, we write select distinct, but this time we're going to pass in 2 columns. So we're going to pass in locality, species ID, and then we have our from clause. Alright, so let's execute that one. So now we get 6 rows returned. So we get a couple more rows than when we just did our select distinct locality by itself. And that's because we have more than one species being counted at the same locality. So for example, if we look at South Georgia Island, we can see we've done species counts for species ID 2, and we've also done species counts for species ID 4 at South Georgia Island. So what this means is that the locality column by itself is not unique, and the species ID column by itself is not unique. So we have duplicates. So we've got 2, 2, 3, 3, Falkland Islands, South Georgia Island, South Georgia Island. But when we combine these 2 columns, they are unique. So the combination of values in each row is unique. So how I like to think about it is if we actually combined these values with, say, an underscore in the middle, those values would be unique. So when we do select distinct and we pass in our columns, then we're going to get a set returned, as we'll have no duplicate rows. Alright, that's it for the tutorial. See you in the next one. Row ordering in SQL. Recall that one of the fundamental aspects of a set is that there is no relevance to the order of the tuples in a set. For this reason, rows in a SQL table conceptually have no definite order to them. Therefore, when you issue a query against the table, do not expect the order to always be the same as it was the previous time you queried the table. Let's go for an example. So here we are selecting employee ID and first name from the employees table. And it looks as though the query result has been ordered by employee ID in ascending order, as we have 1, 2, 3, 4. However, this is not the case. For example, it is entirely possible that later on we issue the same query and the row order could be completely different. For example, we could have got this instead. So now, even though we got a different row order returned, these 2 sets are still considered correct and are still considered to be the same as each other, because in the relational model, the order of elements in a set is of no relevance. And it is an important concept when you are issuing SQL queries against the table as well, because the SQL engine does not guarantee the order in the query result unless we specifically ask it to. For example, the SQL engine could decide to parallelize a query or scan the data in file order rather than index order. So even if you have a primary key or unique index on the underlying table, it does not matter. Do not assume that the query result will be returned in a certain order. However, SQL does provide us with a way of ordering rows in a query result, and we can do that using the order by clause. So let's take a look at that. So at the end of our statement, we can add an order by clause. So now the rows are guaranteed to be ordered by the employee ID attribute. So now the result is not quite considered to be relational. In standard SQL, this is what's called a cursor. Okay, so a couple of things to note about the order by clause. One is it always comes at the end of our select statement. Another thing is that the default order is ascending order. So notice that employee ID is ascending. That is, it is increasing from the smallest value to the largest as we go down the rows that are returned. So we can include ASC keyword if we want, such as this here, which will return the same result as before because ascending is our default order when using the order by clause. If we want to return the rows ordered by employee ID but in descending order, then we can write DESC instead. For example, so now we have the employees ordered by employee ID in descending order. Therefore, we have the employee with the largest value for employee ID returned in the first row, which is Chelsea, as she has an employee ID of 4. We can also order by position of a column in the select clause. So let's have a look at that. So now we have order by 2. Therefore, the rows are ordered by the first name in the default ascending order, because first name is the second column we have specified in our select clause. So we have employee ID, that's our 1, first name, 2. Order by 2, so we're ordering by first name. Although we can order by the position of the column as it appears in the select clause, as we have done so here, this is generally considered to be bad practice. For example, what if at some point in the future we change the order of the columns in the select list, but forget to update the order by clause? So for instance, let's change the order of the columns in the query, but leave the order by as it is. So now we have got the rows sorted by employee ID instead of first name, because employee ID has been specified as the second column in the select clause. So it is much better to write the name of the column in the order by clause. For example, and so now we are ordering by first name, and it will always be ordered by first name, even if we shuffle around the columns in the select clause. Let's look at an example where we are sorting a date data type column. So let's say we wanted to order the employees by hire date and show the most recently hired employees first. We can do this by ordering by the hire date in descending order. So when ordering by a date data type column, I like to remember the saying, later dates are greater dates. This is a helpful way to remember that if we want to show the most recent date first, then we need to order the column in descending order. In this example, we have Chelsea, who is the most recently hired employee, followed by Herb and Vera, and then we have Ben, who was hired back in 2012. Notice that Herb and Vera were hired on the exact same date. Therefore, the order of the rows is not guaranteed to always be returned in the same order. For example, we might run the same query again, but this time get Vera returned before Herb. In this case, in order to guarantee that the order of the rows returned by the query will always be the same, we need to include a column with unique values in the order by clause, which will act as a tiebreaker. So let's have a look at that. Okay, so now we are ordering by two columns in the select clause. First, we are ordering the rows by hire date in descending order. Then for employees who have the same hire date, we are ordering these by employee ID in ascending order. So in this case, we get Chelsea still gets returned first as she is the most recently hired employee, as we are first ordering by hire date in descending order. Then we have Vera and Herb returned, as they are both hired on the same day in 2017. However, we will now always get Vera returned before Herb because we are then ordering by employee ID in ascending order, and she has an employee ID of 1, which is a smaller value than Herb's employee ID. So in summary, we have used employee ID as a tiebreaker, and therefore the ordering is now said to be deterministic, as it will always return what we expect it to. As previously mentioned, ascending order is the default, so we could have left out the ASC after we had ordered by employee ID, and this query would have still returned the same result. One final thing I'll mention is that we can order a column by including it in the order by clause, but we do not have to include it in the select clause. For example, now we have the same ordering as before, as we're still ordering by hire date and then employee ID. However, notice that hire date has been removed from the select clause. This is perfectly valid to do. However, it would be more informative to include the hire date in the select clause as well. Hello and welcome to the limit clause lecture. The limit clause allows us to limit the number of rows returned by a query. And we specify the number of rows we want the query to return in the limit clause. Limit is often used with an order by clause. So for example, let's say we want to write a query to get the top 10 employees who get paid the most. In this example, we would first order the rows by salary in descending order, i.e. highest to lowest, and then we limit the result to 10 rows. The limit clause goes at the end of the query. And note that some databases do not have a limit clause or have a different way of doing the same thing. For example, in Microsoft SQL Server, the equivalent to limit is called top, and this has a different syntax to it. Okay, with that aside, let's take a look at an example. Okay, so here we are selecting some columns from a table called orders, and if we wanted to limit the query result to a certain number of rows, then we can do that by using the limit clause. For instance, let's add a limit clause to return only 2 rows from the table. So at the end of our query, we've just written limit 2. So in this case, the query is limited to 2 rows, which get returned, and these are returned in an undefined order. So this can be useful in situations where we have a very large table with thousands or millions of rows in it, but you might want to look at maybe 100 rows from the table to get some idea about the data in the table. However, typically the limit clause is most useful when used in conjunction with an order by clause. For example, let's say we wanted to return the 2 most recently placed orders. We can do that by writing the following query. So now after the from clause, we have added a order by clause, and we have order by, order date, descending. And this will order the rows from the most recent order to the oldest order date. And after the order by clause, we have limit to, so we get the two most recently placed orders. And in the query result, this query gives us order IDs 107 and 103. So 107 was placed on the 30th of July 2020, and 103 was placed on the 22nd of June 2020. And this here is the language neutral way of formatting dates, and that's to have the year first, followed by the month, and then the day. Okay, if we look at the data more carefully in the orders table, we can actually see that there were two orders placed on the 22nd of June. So this means that this query is not deterministic. In other words, the query is not determined to return the same result. So this query filtered two rows, but if we ran the same query again, we might get a different two rows returned. In this case, we might get order ID 104 returned, as that has the same date as order ID 103. So this is something to be aware of when using the limit clause in MySQL. In some other databases, there is an option to limit the result with ties, but MySQL currently doesn't have the with ties option. However, there are some workarounds, one of which is to use the rank window function, and we will be going through window functions later in the course. Okay, so that's it for the limit lecture. See you in the next one. Hello everyone, and welcome to the order by challenges. Okay, let's go to the first challenge. So for the first challenge, you are to write a query that returns all employees ordered alphabetically by their last name from A to Z. Let's take a look at the hints. Query the hcm.employees table and include an order by clause in the query. And this hint also applies to all the other challenges in the lecture. So all the challenges will involve using the order by clause. Okay, let's look at the second challenge. In the second challenge, you are to write a query that returns all employees ordered by salary from highest to lowest. And for the third challenge, write a query to return all employees ordered by the most recently hired to the longest serving. Okay, let's go to the next challenge. For the fourth challenge, you are to write a query to return all employees ordered by department ID in ascending order. So remember that ascending order is from smallest to biggest, and then within each department ID, you are to order by salary from highest to lowest. Okay, moving to the next challenge. So for the fifth and final challenge, you are to write a query to return the employee ID, first name, last name, and salary for the top 10 employees who get paid the most. Coming up is the hint. So remember to use an order by clause followed by the limit clause for this particular challenge. Okay, so have a go at doing those 5 challenges, and in the next lecture, we'll go through the solutions. Okay, so now let's go through the solutions to the order by challenges. And so for the first challenge, we were to write a query that returned employees ordered alphabetically by their last name from A to Z. So for this query, we just write select star from hcm.employees. Then we have our order by clause. So we write order by last name ASC. So ASC stands for ascending order. So let's click in the query, execute that, and there we have it. We have all our employees ordered from A to Z. Another way we could have written this is we could have written just order by last name, and we didn't need to include ASC because ascending is the default used by MySQL. So if we had just executed that query, it would have given us the same result. Okay, let's move to the second challenge. So for the second challenge, you were to write a query that returned employees ordered by salary from highest to lowest. So this time in the order by clause, we have order by the salary column, and we're saying DESC for descending. So descending is where you start high and then move down. think about if you descend from a mountain, you're moving down the mountain. So in this case, we're going to have the highest salary first, and then we'll move to the lowest. Alright, so let's execute that query. And if we have a look at the salary column, we can see that the highest earner is Jack Bernard, followed by Don, and then Judy. Okay, let's move to the third challenge. So for this challenge, you were to write a query that returned employees ordered by most recently hired to longest serving. And this time in the order by clause, we're going to be ordering by the hire underscore date column. So that was the date that the employee was hired. And we're going to say descending order. So remember that later dates are greater dates. So this will turn the most recent date first, and then progressively move to the longest serving employee. So let's click in the query and execute it. So the most recent hire was Peter Owen on the 12th of the 10th, 2019, and then our longest serving employee will be at the very end here, and that's Irene, and she's been with the company since the 22nd of February 2001. Okay, let's move to the fourth challenge. So for this challenge, we were to return employees ordered by the department ID in ascending order, and then within each department ID, we wanted to order by salary from highest to lowest. So this time in the order by clause, we have order by department ID in ascending order, ASC. Then we do a comma, and then we do the second column we want to order by, which is the salary. So we say salary, and this time it was descending order. So let's just click in there, execute it. So now we have everything ordered by department ID. So first of all, we've got some nulls for department ID, but if we scroll along, okay, so we've got department ID 30. So we'll have all the rows in department ID 30, and then within department ID 30, we're going to be ordering by salary. So Diana Coleman is the highest earning employee in department ID 30. And then after we've done all department ID 30, we move to the next department and so on. Another way we could have written this query is by removing the ASC, because that is the default. So we could have just written order by department ID, comma, salary, descending. Okay, so let's move to the next challenge. And so for the fifth challenge, you were to return the employee IDs, names, and salaries for the top 10 employees who get paid the most. So this time we have select employee ID, first name, last name, salary from hcm.employees. And we're doing an order by salary in descending order. And then after the order by clause, we have a limit clause. So we just write limit 10. So that's going to limit it to the top 10 employees who get paid the most. So let's execute that. And given here are our top earning employees in the organization. Alright, so that's it for this lecture. See you in the next one. Welcome to this lecture on the where clause and three valued logic. Okay, let's get into it. Here we are selecting a few columns from a table called suppliers. And this query returns 6 rows. We have the state and city information for each supplier. However, notice that supplier IDs 5 and 6 have null for the state column. In SQL, a null represents the absence of data. A null is not a character string, blank space, or a 0. You can think of a null as being something which is unknown. In this case, we could say that we do not know what state supplier IDs 5 and 6 are in. Perhaps Oxford City does belong to a state, but it just hasn't been inserted to the table. Or perhaps Oxford City does not belong to a state. Either way, we don't know just by looking at the data in this table, as all we have are some nulls. Because a null is something unknown, then this means that a null does not even equal another null. Often people will refer to nulls as null values. But strictly speaking, this is incorrect, because a null is not a value. Instead, it marks the absence of a value. In saying this though, even myself sometimes I will say null values, even though this is not strictly speaking correct terminology. The correct term is to just say nulls or null markers. Okay, we will talk a bit more about nulls in just a moment, but first let's look at how we can filter rows returned by a query by using the where clause. Okay, let's say we want to return only the suppliers who are from Texas. We can do that by using the where clause. So after the from clause, we write where state equals Texas. And we enclose the word Texas in single quotation marks because it is a value in a character data type column. Okay, so in the query result, we get 2 rows returned. These are suppliers 3 and 4. And I've grayed out the rows that were not returned by the query. Okay, so let's say we want to write a query to return all the suppliers that are not in Texas. We can simply change the equals to not equals. To do not equals, we use a pair of angle brackets. Let's show that now. Okay, so now we have supplier IDs 1 and 2 returned. Notice though that suppliers 5 and 6 were not returned by this query, even though they do not have a value of Texas for the state column. This is because suppliers 5 and 6 have nulls for the state column. Technically, this query is correct, because we don't know if suppliers 5 and 6 are in Texas or not. If we want to return the nulls in the state column, then we need to modify the query by adding on an OR operation to show that. So now we have where state does not equal Texas or state is null. Since we're using the OR operator, this means that the predicate evaluates to true if at least one of the conditions is met. In a lecture later on, we will be taking a closer look at the OR operator. Okay, so we get 4 rows returned, and this includes the rows where state is null. Notice that we need to write is null. We do not write equals null. To demonstrate this, let's change the query by removing the first condition so that we only return rows where state is null. Okay, so now we get 2 rows returned by this query. If we tried to write equals null instead of is null, then we would get the following. So this query would run successfully, but it would always return 0 rows. So this is not the result we intended. The reason why this query returns no rows is because a null is not equal to anything else, including another null. This is because something that is unknown cannot be equal to another unknown. So in your queries, you should never write equals null. Instead, we write is null. Welcome back. In this tutorial, we'll go through how we can replace nulls in our queries. Let's get straight into it. So here we are selecting some information from a table of employees. And let's say we want to add on an expression in our query where we add together the salary and bonus columns. Let's do that. Okay, so now in the last expression in the select clause, we have salary plus bonus as total amount. So if we look at the first few rows, the total amount looks good. So we've got for James 90,000 plus 5,000, total 95,000. But if we look at the last couple of rows for Sarah and Jonathan, they have null as the total amount. So if we take Sarah for example, she has a salary of 85,000, but she's got null for the bonus column. And this is also the case for Jonathan. And so remember that any mathematical operation involving a null will always return a null. So 85,000 plus null is null. So this is not the result that we wanted. What we can do in this situation is use a function called the coalesce function to replace the nulls with another value that we specify. In this case, we want to replace the nulls with a 0. Okay, let's do that. So if we look at the syntax for the coalesce function, so the coalesce function accepts 2 or more expressions, and it will return the first non-null expression. So in this example, we have 2 expressions that we've specified in the coalesce function. So we've got salary plus coalesce, and then within our parentheses here, we specify our expressions. The first expression is the bonus column, and the second expression is just the value 0. And of course we put a comma between each expression. Because the coalesce function returns the first non-null value in a series of expressions, this means that in this case, if the bonus column is null, then these rows will get replaced with zeros, as 0 will be the first non-null expression. So what happens now for Sarah and Jonathan is that we've got 85,000, and this null gets replaced with a 0, so we're going to have 85,000 plus 0, and then we get the total amount we wanted, 85,000. And we get the same calculation happening for Jonathan as well. Okay, let's have a look at a situation where we would specify more than 2 expressions in the coalesce function. Here we are selecting some columns from a table of emergency contacts. So these are the emergency contact phone numbers for each employee. And we have the contact name, their home phone, cell phone, and work phone. Now we are going to use the coalesce function to return the first non-null phone number, and if all the phone numbers are null, then we will just return the string literal NA, which is short for non-applicable. Okay, so what this coalesce function here is doing is that it is going row by row, and it's returning the value from the first non-null expression for each row. And in this case, we are calling the expression phone. So we just have as phone at the end. So on the first row, for employee ID 1, whose contact is Brianna, in our coalesce function, we are first looking at the home phone. And in this case, Brianna has null for home phone. And then we move to the second expression, which is the cell phone. And the cell phone has a value in it, a non-null value. So because Brianna does have a cell phone number, this is what gets returned by the coalesce function for this expression here. So on the next row, we have Ashley, who has null for both the home phone and the cell phone. But Ashley does have a work phone, and so that's what gets returned by the expression. So we keep doing this for each employee. And I just want to draw your attention to the last employee, which is employee ID 5. And the emergency contact for employee ID 5 is Christy. And notice that Christy has a null for the home phone, cell phone, and work phone columns. And so this means that this coalesce function here is going to move all the way to the first non-null expression, which is this text literal NA. So what gets returned is the text string NA for employee ID 5. And NA just stands for non-applicable. Okay, so that's it for this lecture. See you in the next one. Welcome back. Now we're going to take a look at the different comparison operators we can use in the conditions we specify in the where clause. So here we have some different comparison operators. So we have equals, and we've got 2 ways we can do not equals. One way is the less than symbol followed by the greater than symbol. So this means not equals. And another way is we can do exclamation mark equals, which also means not equals. Then we have the less than operator, and one way I like to remember the less than operator is it's sort of like an L but on a bit of an angle. And then we have less than or equal to, we have greater than, and greater than or equal to. Okay, let's look at some queries where we use these comparison operators. Here we are selecting a few columns from a table called products, and we have the category and price of each product. Let's say we want to write a query to return only the products that have a price less than $12. Let's do that now. All we need to do is to write where price less than 12. This returns two rows, product ID 4, which has a price of $10, and product ID 8, which has a price of $5. Notice that product ID 5, which has a price of exactly equal to $12, was not returned. This is because this query is filtering only products that are less than 12. If we wanted to include this product, then we would need to change the query to less than or equal to 12. Let's do that. Okay, so we now have returned products where the price is less than or equal to 12. And we get 3 rows returned, including product ID 5, which has a price of exactly equal to 12. Let's now return all products which have a price greater than $21. Now we have where price greater than 21, and we have 4 rows where this condition evaluates true. Notice that product ID 3 is not returned because it has a price of exactly equal to $21. Similar situation to last time, so we can change the query from greater than to greater than or equal to. Let's show that. Now we got all products returned which have a price greater than or equal to $21. Another thing we can do is that we can return rows that fall within a specified range by using the between operator. Let's look at an example of that. Now we have in the where clause, we've got where price between 10 and 21. So this is going to give all rows which have a price which is anywhere between $10 and $21. And the between operator is inclusive of the lower and upper values that we specify. So it's going to include products with a price of $10 or $21. So in this case we get 3 rows returned. So this query is the same as if we wrote where price is greater than or equal to 10 and price is less than or equal to $21. The AND operator is where both conditions need to be met in order for a row to evaluate true and be returned. Later on we will be taking a closer look at the AND operator. Hello and welcome to the next set of challenges for you. So these challenges all involve using the where clause to filter rows. Okay, let's look at the first challenge. So for the first challenge, you are to select products from the OES.products table which have a price greater than $100. Moving to the second challenge. So in this challenge, you are to select all orders from the OES.orders table which have not yet been shipped. And the hint for this challenge is that these are orders where the shipped date is null. Moving to the third challenge. Okay, so for the third challenge, you are to select all orders from the OES.orders table which were placed on the 26th of February 2020. Coming up is the hint. So in MySQL, when querying a column of data type date, you can use the format year, month, day, all in digits. So for example, the 25th of April 2020 would be written as 2020-0425, and we put this value within single quotation marks. Alright, let's move to the fourth challenge. Alright, for this one you are to select all orders from the OES.orders table which were placed on or after the 1st of January 2020. Coming up is the hint. So when using comparison operators with dates, an older date is considered smaller than a newer date. So for example, the date the 1st of January 1990 is considered a smaller value compared to the 1st of January 2020. And I like to remember the saying that later dates are greater dates. Okay, so have a go at doing these 4 challenges, and in the next lecture we will go through the solutions. Welcome back everyone. Now we'll go through the solutions to the where clause challenges. So before doing the first challenge, we're just going to select all the columns from the products table, and that's just to get an idea of what columns we have in the table. So we've got select star from oes.products, so I'm going to run that. Okay, so this gives us a table of products, and for the first challenge we were to select all products which have a price greater than $100. So the column that we're interested in using is called list price or list underscore price. So this is what we're going to filter on in the where clause. So in the solution we have select all columns from oes.products where the list price is greater than 100. So we'll click in there, execute it, and we can see that we get 55 rows returned. So we have 55 rows which have a list price greater than $100. Okay, moving to the second challenge. So for the second challenge, we were to select all unshipped orders, and this is where the shipped date is null. So let's just select from the table again. Okay, so for the oes.orders table, we have these columns here. And so the one we're interested in is called shipped underscore date. And so in the where clause, we're going to say where shipped date is null. And remember that we never write equals null, we only write is null. So if we had written equals null, we would have got no rows returned because nothing can be equal to a null, including another null. And for that reason, we always need to write is null, never write equals null. So let's execute that query. Okay, so these are all the unshipped orders which don't have any ship date in them, they just have nulls, and we've gotten 21 rows returned. So 21 orders have not been shipped yet. Okay, so let's move to the third challenge. So for this challenge, we're to select all orders placed on the 26th of February 2020. So now in the where clause, we're going to have where order date is equal to, and then in single quotation marks, we first write the year, 2020, and then we write the month, 02 for February, and then we write 26 for the day. So this is the language neutral way of writing dates, which is year, month, day, all in digits. Okay, so let's execute that query, and we get 6 rows returned. These are all the orders placed on February the 26th, 2020. Moving to the next challenge. Okay, so for the fourth and final challenge, we're going to be selecting orders placed on or after the 1st of January 2020. So now in the where clause, we have where order date, and then we've got greater than or equal to, and then we specify our year, month, day. Okay, so let's execute that, and we have 270 rows returned. So these are all of the orders placed on or after the 1st of January 2020. Okay, so that's it for the lecture. See you in the next one. Welcome back everyone. In this lecture, we're going to be introducing the topic of collations and pattern matching. Let's get straight into it. So first of all, what is a collation? So a collation is simply a set of rules that defines how to compare and sort character strings. Each collation in MySQL belongs to a single character set, and every character set has at least one collation, and most have 2 or more collations. A collation orders characters based on weights, and characters with equal weights compare as equal. For example, in a case-insensitive collation, then a lowercase a is equal to an uppercase capital A. Alright, let's now go through some examples. Okay, so here we have a table of products, and we have product ID and product name. Let's say we have the following task. Write a query to return products called USB hub. Let's show how to do that. So in the where clause we have where product name equals USB hub, and we have enclosed the character string USB hub in single quotation marks as it is a text string. In this case, 3 rows are returned when using a case-insensitive collation. Note that the rows with the grayed out text are the ones not returned by the query. Okay, so notice that this query returned a case-insensitive result. In other words, it didn't matter if the text was uppercase or lowercase letters. As long as it had the text string USB hub, then that row was returned. This is because the product name column has been set to a case-insensitive collation. Recall that a collation is simply a set of rules that define how to compare and sort characters in MySQL. Also, collation can be set at a database, table, or column level. In this case, the collation for product name column is called UTF-8 MB4 0900 ASCI. So first, UTF-8 is the character encoding scheme. The MB4 means that each character can store up to a maximum of 4 bytes. 0900 is the Unicode collation algorithm version, and then we have AS, which stands for accent sensitive. So this character here is an example of an accented character as it has a dash above it. So for an accent sensitive collation, an accented character, as shown here, is not equal to a standard A. Okay, so then finally we have CI, and CI stands for case insensitive. Case insensitive means that it does not distinguish between upper and lowercase letters. In other words, an uppercase letter is treated as being the same as a lowercase letter when using a case insensitive collation. So we can say that it is insensitive to the case. Doesn't matter if it's uppercase or lowercase, treats it as the same. To find out what collation is being used at a column level for a particular table, we can find this by querying a system view in the information schema. So let's take a look at that. Okay, so in this query, we are querying a system view called columns in the information schema. The information schema has a series of system views and is one of several methods that MySQL provides for obtaining metadata. Metadata is data that provides information about other data. In this case, we are getting metadata information about the columns in the products table. So in this query, we are selecting some columns from information schema.columns, where table schema equals DBO and table name equals products. So in this particular example, the products table belongs to a schema called DBO. And note that this example is not the same as the products table in the OES database. If we were querying the products table in OES database, we would instead need to change the table schema from DBO to OES. With that aside, what this query is giving us is 2 rows which give details on the columns in the products table. Okay, so on the first row we have product ID, which has a data type of int, short for integer, which are whole numbers, and there's no collation for this particular data type, hence the collation name is set to null. And then on the second row we have the product name column, has a data type of varchar, and this has a collation of UTF-8, MB4, accent sensitive, case insensitive. Okay, let's now go back to our previous query. So we got 3 rows returned when searching for the string USB hub, since this column is using a case insensitive collation. Alright, let's go back to select all rows from the table. So now our new task is to return products where the product name equals USB hub, i.e. USB is all uppercase letters and the hub is lowercase. So in other words, we want to do a case sensitive pattern match. And we can do this by changing the collation within the context of the query. Let's show that. Okay, so we have our where clause, where product name equals USB hub, and we've specified how we want the case. And then after this, we're going to use the keyword collate, and then we give the new collation that we want to use. So in this case, we are specifying a case sensitive collation with CS. So now this query returns one row for product ID 7, as it has exactly the case that we want. Okay, let's show all the rows again. In SQL, we can do wildcard searches on character data using the like operator. So let's say we had the following task. Return products which contain the word tablet anywhere within the product name. We can achieve this by writing the following query. So now in the where clause we have where product name, and then we have the keyword like, and following that we have our character string in single quotation marks. But this time we're putting a %sign on either side of the character string we're searching for. So this will evaluate to true for any rows which have the word tablet anywhere within the product name. The %sign is a wildcard which represents 0 or more characters. So in this case, since we have placed the %sign on either side of the character string tablet, it could have 0 or more characters, any characters, either side of this word, and this would evaluate true as long as the product name contained the character string tablet. If instead we wanted to return all rows which started with the word tablet, we can change the query to this. So now we get 3 rows returned, and these are where the product name starts with the word tablet. So in the where clause we have where product name like, and then we have tablet %sign, all in single quotes of course. So this is going to search for the word tablet at the start of the product name, and because we have a %sign at the end, this means that the string tablet can be followed by 0 to any number of characters. So we get 3 rows returned in this case for tablet, tablet x2000, and tablet x3000. If we wanted to return products that end in the word tablet, then you guessed it, we can put the %sign just at the start, for example. So now we get rows returned which end in the word tablet, and we can have any number of characters before the word tablet. The character string we are searching for is also called a literal. In SQL, a literal is some constant number or character string, which is typically not represented by an identifier. In summary, we can use the %sign as a wildcard for any number of characters, and we can place it either side or both sides of the string that we want to search for. Okay, that's it for this lecture on an introduction to collations and pattern matching. In the next one, we'll be covering some more pattern matching techniques. See you there. Hello and welcome to the second lecture on pattern matching. Let's get started. So here we are selecting from a table of products as shown on the left. Now let's say we have the following task. Return products where the second character in the product name is the letter X. So if we want to have a wildcard for a certain number of characters, then we can use underscores. So in this case, we can write the following query. So now in the where clause, we have where product name like, and then in single quotes, we have underscore X %sign. So the underscore represents a single character. So that means that the first character can be any character, and the second character in this case needs to be the X. And then we have the %sign, so we can have any number of characters following the X. So we have 2 rows which meet this condition, which are product IDs 9 and 10. And we can see that we have an X as the second character in their respective product names. Okay, let's now go back to selecting all rows from the table. Alright, let's say we have been given a new task. Return products which contain the character string used underscore tablet. Now if we try and put this in a wildcard search with %signs on either side, we're going to get a problem, and that's because SQL is going to interpret the underscore in the string as a single character wildcard rather than an actual underscore, for example. So we get 2 rows returned, and notice that product ID 5 gets returned even though it does not have an underscore between the used word and tablet word. Instead, it just has a blank space. So this row gets returned because SQL is interpreting the underscore in the character string as a single wildcard character, and not as an actual underscore. So this query is not giving us what we want. If we want to search for an actual underscore character in a string, then we can do so by using an escape character and the escape keyword. This is best shown by example. So this query gives us the result we wanted, and in this query we are using an exclamation mark as our escape character, and we put the exclamation mark before the underscore in our string. So this tells SQL to interpret the underscore as an actual underscore and not as a wildcard character. So to summarize, we have where product name like, and then within our single quotes, again we've got our %sign on either side. So we're searching for this string anywhere within each product name. And in this case, we're using an exclamation mark as our escape character. So we put it before the underscore. And then we have the keyword escape. And then in single quotation marks, we specify what we want our escape character to be. So in this case, we've used an exclamation mark, but we could have used any character as an escape character. For instance, we could have used a question mark instead of an exclamation mark, for example. So this gives the same result. And just as a note, the important thing is that you pick a character that does not appear in the column being searched on for your escape character. Alright everyone, that's it for the lecture. See you in the next one. Welcome to the pattern matching challenges. Let's go straight to the first challenge. For this challenge, you are to select countries from the HCM.countries table, which start with the letter N. Okay, so here comes the hint. So use the like operator and the % wildcard. And note that this hint also applies to the other challenges in this video. Okay, let's have a look at the second challenge. For the second challenge, you are to select customers from the OES.customers table who have a Gmail email address. And now for the third challenge. Select product names from the OES.products table which contain the word mouse anywhere within the product name. Okay, so give those few challenges a go, and next up we will go through the solutions. Alright, let's now go through the solutions to the pattern matching challenges. So for the first challenge, you are to select all countries which start with the letter N. So because we're doing a wildcard search, we're going to use the like operator. So we have where country name like, and then in single quotation marks we have N %sign. So the % sign wildcard means we can have 0 or more characters, any characters, after the first character, which needs to be an N. Okay, so I'm just going to click in here and execute the query. And we have 4 countries in the countries table starting with the letter N. And in this case, we could have actually used a lowercase n and we would have got the same result. For example, we could have had where country name like, a lowercase n, then %sign. So if I execute that query, we get the same result. And this is because the country name is using a case insensitive collation. And to get the collation, we can query the information schema columns table. So just to quickly show you that, if I go up to the top of this script, so this query here is going to give us information on the collation for each column in the HCM.countries table. So I'll just click in the query and execute it. So we can see here that the country ID column has a data type of int, so it's an integer, doesn't have a collation. The country name column has a data type of varchar, and here is the collation name here, and we can see we have CI at the end here for case insensitive. Alright, let's now move to the second challenge. So for the second challenge, you were to select all customers who have a Gmail email address. So this time we're going to put the % wildcard at the start of the string. So basically this means we can have anything at the start of the string for the email column, but we want to make sure that they end in @gmail.com. So we have %wildcard @gmail.com. And that's because all the Gmail email addresses will end in this suffix here, gmail.com. Okay, so just click in the query and execute it. So these are all the employees who have Gmail email addresses. Okay, let's move to the third challenge. So this one here, we were to select all product names which contain the word mouse. So this one here, we want to do a wildcard, search for the mouse anywhere within the product name. So we're going to have select product name from oes.products, where product name like, and then we put the %wildcard on either side of the search string mouse. So we click in here and execute it. And as you can see, we get 4 products returned, and each product has the word mouse somewhere within the product name. Alright, that's it for the lecture. See you in the next one. Welcome to the MySQL Data Types lecture. MySQL database supports a lot of data types, but in this video, we are just going to look at the most commonly used ones. Alright, let's get started. In a SQL table, each column has a data type. A data type specifies the type of data that a column is allowed to hold. So for example, a column with a data type of int can only hold integers, i.e. whole numbers. Okay, let's take a look at the main classes of data types. So the main classes of data types in MySQL are string, numeric, and date and time related data types. Note that MySQL supports many more data types than I have listed here. For example, it has data types to store binary strings and geometry data. However, the ones we are focusing on here are the ones that you will most likely encounter when working with MySQL database. When we create a table in MySQL, we need to specify the data type of each column. So we need to make sure we choose the most suitable data type for each column. However, the focus of this course is purely on querying MySQL, and we will not be creating any tables. But even though we are just querying data, it is still important to know about data types, particularly if we are using MySQL's built-in functions. Okay, let's take a look at these string data types. So the two main string data types are varchar and char. First we have the varchar data type. This can be used to store variable size character data. And notice that after the word varchar, in parentheses we have this letter n. This is where we pass in a number, and this number n defines the maximum number of characters that a column can hold. So we might have varchar 50, and that would mean the column could hold up to 50 characters. Now there are some limits on this length, but we won't get into that in this course. Okay, so the other commonly used string data type is char. Char holds strings which are all the same length, so it stores fixed length string data. So if we use char for a column, then every value in that column is going to take up the same length. And note that for fixed size character strings, such as char, if we insert a character string that is shorter than size n, MySQL will automatically pad the string with blank spaces. This is to maintain the fixed length size of each character string. On the other hand, variable length character strings, such as varchar, store strings up to n in length. These strings are not padded with spaces if the variable length is less than the specified length. Okay, let's take a look at the integer data types. Integers are whole numbers, and in MySQL we have 5 different integer data types as shown here. So we have tiny int, small int, medium int, and big int. And also given here is the possible range for each of the data types. And note that each data type has a different range depending on if it is signed or unsigned. Note that unsigned is a setting that can be placed on a column. If a column is unsigned, then this means that it cannot store negative numbers. Therefore, an unsigned type has more room to hold twice as many positive values as a signed type. However, we cannot insert any negative number into an unsigned column. Okay, let's take a look at the decimal data type. The decimal data type is a numeric data type that has a fixed precision and scale, which is specified within parentheses. So this one is best shown by example. So in this example, we have a column called site measurement of the decimal data type, which has a precision of 8 and a scale of 5. Precision is the maximum number of digits that can be stored. The precision number includes digits on both the left and right side of the decimal point. Scale is the number of digits that are stored to the right of the decimal point. So in this case, the largest value that a decimal 8,5 data type column can hold is 999.99999. So this means that 5 of the 8 digits are reserved for after the decimal point. 8 minus 5 is 3. So in this case we only have 3 digits allowed on the left hand side of the decimal point. A common mistake I've seen people make is they think that the precision is the number of digits to the left of the decimal point, but that is not the case. In actual fact, precision refers to the total number of digits, and therefore we need to minus the scale from the precision if we want to work out how many digits we can have on the left of the decimal point. Something else to be aware of is that the decimal data type is the same as the numeric data type. Decimal and numeric are synonyms that can be used interchangeably. Okay, let's take a look at the float data type. The float data type stores floating point numbers. The term floating point is derived from the fact that there is no fixed number of digits before or after the decimal point. Therefore, the decimal point can float. Float is an approximate number data type. Alright, let's take a look at the date and time data types. The date data type is used for values with a date part but no time part. MySQL displays date values in the year, month, day format. So we always want to make sure our dates are in this format. On the other hand, we have the time data type, and this stores only a time part. MySQL displays time values in hour, minute, second format. MySQL also has a couple of data types that store both the date and time parts. Let's now take a look at those. Both the date time and timestamp data types can store values that contain both date and time parts. And both these data types are in year, month, day, hour, minute, second format. The supported range for the date time data type is 1st of January year 1000 to the year 9999. We have a bit of a narrower range for the timestamp data type, so that will go from 1970 to the year 2038. And note that this isn't stored in UTC time. So timestamp values are converted from the current time zone to UTC time for storage, and then they're converted back from UTC time to the current time zone for retrieval. So in this course we're not really going to be using these two data types, but it's important just to be aware of them. Alright everyone, that's it for the data types lecture. See you in the next one. Welcome back. In this lecture we will be introducing the topic of aggregate functions. Aggregate functions are commonly used together with the group by clause, where a value is returned for each group of data. We will be taking a look at the group by clause in the next lecture. In this lecture, we are just going to use aggregate functions without a group by clause. Alright, let's get started. In SQL, we have two main types of functions, and these are scalar functions and aggregate functions. Scalar functions are ones which operate on one row at a time. Scalar functions return a value for each row. For example, the upper function will convert values in a column to all uppercase characters. Aggregate functions are functions that return a single value for potentially multiple rows. In other words, aggregate functions return a single value for a group of data. For example, the max function will return the largest value from a set of values in a column. Okay, let's go through some query examples. So here we have a table called properties, and we have some details for each property, such as the street number, and if the street address has a suffix, and the property value. Let's say we want to write a query to return the lowest property value. We can do that by using the min aggregate function. So let's look at that. So in our query, we have select min, open parenthesis, and then we pass in a column, in this case the prop value column, close parenthesis, Then we assign an alias by using as, and the alias name, we're calling it minimum prop value. And on the next line we have from properties. So this returns one row, which is the minimum value, i.e. the smallest value in the prop value column, which is currently $350,000. You might be wondering, how can we return the other attributes of the property which has the minimum value, such as the property ID? We will be looking at how this can be achieved using a subquery in a lecture later on. Okay, so if we instead wanted to return the maximum property value, we can use the max aggregate function, for example. And the maximum property value is 600,000. If we wanted to return the total value of all properties, then we can use the sum aggregate function. For example, the sum function simply adds up all the non-null property values. In this case, the total value of all properties is 1.83 million. Now let's look at the average aggregate function. So the average aggregate function is just written as AVG. And in this query, we're calculating the average property value. The average is also referred to as the mean. Again, the nulls are ignored. So to calculate the average, it sums up all the non-null values and divides by the number of rows which are not null. In this case, we can see that the prop value column has 4 rows which are not null, so it divides the total, the sum of the property values, by 4. Nulls are ignored by all aggregate functions except for count star or count asterisk, which we will see in just a moment. But first, let's look at where we apply the count aggregate function to a specific column. For example, in this example, we are counting the number of non-null values in the column called suffix, and we get a count of 2, and this is for these 2 rows here, which have a value of A and B. If instead we wanted to count all rows in a table, then we can use count asterisk, or as I like to say, count star. For example, this query returns a value of 6 as we have a total of 6 rows in the properties table. Let's now look at count distinct. So here in the first expression, we are counting the number of values in the street num column, and we get a total of 6. In the next expression, we have count open parenthesis distinct street num close parenthesis, and since we write the distinct keyword before the column name, what this is going to do is it's going to count the number of distinct, i.e. unique values in the street num column. And as you can see, this returns a value of 5. Since these 2 numbers here do not match, this indicates that duplicate values exist within the street num column. And we can see from the street num column that sure enough we have the value of 21 repeated on more than one row. When we use count distinct, then this repeated value is only counted once. Welcome back everyone. In this lecture we are going to use aggregate functions in grouped queries using the group by clause. Let's get started. So here we have our properties table, except this time we are showing some different columns from this table. So we have the property zone, which is called prop zone, and we have a column called occupied, and this column indicates if the property is occupied or not, and we have a column called area underscore SQM for square meters. So this is the size of each property in square meters. So let's say we want to write a query to get the total area in square meters for properties within each property zone category. We can achieve this by writing the following query. So we have select prop zone, comma, sum area square meters, and we are aliasing this aggregate function as total area square meters. And we have from properties, group by prop zone. So what is happening is that the group by gets processed before the select list, and we are grouping the data by the property zone. And for each unique property zone, we are calculating the sum of the area square meters for each property belonging to that zone. So for example, one of the groups is where prop zone equals commercial. So in this group, we get the sum of 800 plus 500, which gives us a total of 1300 in our query result. The other group is where property zone equals residential. In this group, we sum up all the non-null values for the area square meter column, and this equals 1375 as given here in the query result. Note that the only items allowed in the select clause of a select statement that includes a group by clause are columns that are specified in the group by clause or are aggregate functions. So in this case, since we are grouping only by the prop zone column, this is the only column we can have in our select clause. Any other columns must be part of an aggregate function. So for example, we have area square meters, but it is within the context of the sum aggregate function. So we could do any aggregate function in the grouped query. For example, instead of doing sum, let's do the count of properties, and we'll do the count of properties by the occupied column. Okay, so now we are grouping by the column called occupied, and this time we are applying the count aggregate function. In this case, we use count asterisk, and this is going to count all rows in each group, including nulls. The occupied column has 3 groups. One where it has a value of yes, so there are 3 rows where occupied has a value of yes, so the count is 3 in the query result. We have 1 no, and we have 2 nulls. So count star or count asterisk will count the nulls. If we say count occupied, then this will not count the nulls, and instead will return a 0. Let's add that one in. Okay, so now in this last expression here, we have count occupied as occupied count, and we can see that it only counts non-null values, and it returns a 0 where occupied category is null. So far we have only been grouping by a single column. Let's look at a scenario where we group by multiple columns. So let's do a query where we group by both the prop zone column and the occupied column, and we will sum up the area in square meters within each group. So now we are grouping by multiple columns, i.e. both prop zone and occupied. We are telling SQL to group all rows that share the same value for these 2 columns. As we can see from the query result on the right, we have 4 groups. Notice that in this example, prop zone no longer has unique values in the query result. However, prop zone and occupied columns combined give unique combinations of values. Each group of columns, as specified in the group by clause, is represented by a single row in the query result. In one of the groups, we have where property zone equals commercial and occupied equals yes. So in this group, SQL sums together 800 plus 500, which is 1300 in the query result. Then we have residential and yes. Then we have the combination of residential and no. And again, this is just one row in the source table. Next, we have the combination of where property zone is residential and occupied is null. We have two rows in this group in the source table. And notice that the area square meters is null for one of these rows. This null is ignored by the sum function, so the end result is just 250 for the row which has a non-null value. Hello everyone, and welcome to this lecture on the having clause. Let's get started. The having clause is used to filter groups. If we compare it to the where clause, the where clause filters rows, whereas the having clause filters groups of rows. So with a where clause, we evaluate some condition or conditions, which is our predicate, but we evaluate this for each row in the table. In contrast, for the having clause, we evaluate some condition for each group of rows. Therefore, the having clause is written after a group by clause. So first we use the group by clause to group the rows, and then after that we have the option of using the having clause to filter those groups based on some predicate. Aggregate functions can be used in the having clause. Because the having clause is evaluated after the data has been grouped by a group by clause, this means that we can put aggregate functions in the having clause. Note that we cannot do this with the where clause condition because the where clause is operating at a row level. Let's have a look at the basic syntax for a query which includes a having clause. In this case, we are grouping by column 1 in the group by clause. So this means that we can include column 1 in our select clause, and we are putting column 2 in an aggregate function. Recall that if we are using a group by clause, then we can only put a column in the select clause if we are grouping by that column, or it is within the context of an aggregate function. Okay, so we have our from clause, we've got an optional where clause, group by, and last of all we have the having clause. So we specify the having clause after the group by clause, and in the having clause we can specify some condition, which is typically where we would put an aggregate function. Okay, let's have a look at a real example. So here we have a table called property owners, and each property is identified by the property ID attribute. And note that one property can have one or more owners. For example, property ID 101 is owned by both Arnold and Camille. So we have 101, 101. So let's say we have the following task. Return the owner count for properties which have more than one owner. We can achieve this by writing the following query. And this query gives us the result. So we have two properties which have multiple owners, and these are property IDs 101 and 104. So what we are doing is we are grouping the rows by the property ID column, and then we are counting the number of rows in each property ID group. So let's show that. Okay, so on the left here we have the count per property ID group. So we have 2 rows for property ID 1, 1 row for 102, same for 103, and we've got 3 rows for property ID 104. And then after we do the group by, we then have the having clause. So in this having clause, we have having count asterisk greater than 1. So we are using the count aggregate function, and we are saying return only groups which have a count greater than 1. This will filter the groups, and we are only keeping the groups which have a count greater than 1. Therefore, property IDs 102 and 103 get excluded because these two properties, they each only have one owner. We then get left with property IDs 101 and 104. 101 has 2 owners, Arnold and Camille. 104 has 3 owners, David, Ashley and Carrie. So this is quite a useful query to know, especially to find duplicates in a single column. Alright, thanks everyone. That's it for the lecture. See you in the next one. Hello and welcome back. In this lecture, we are going to cover logical query processing order in MySQL. This is also known as the conceptual order, as it is the conceptual order that the various SQL clauses are evaluated in. Knowing this order will help you to write queries correctly. Okay, let's get started. Okay, so in the left box here, we have what is called the keyed in order. And this is the order that we need to type the various clauses in. This is essentially the same in all dialects of SQL. As we're used to, we write the select clause first, then followed by the from clause, then we have the where clause, then group by, having, and finally we write the order by clause last. Okay, if we have a look at this middle box here, we have MySQL's logical query processing order. And this is the conceptual order that MySQL processes the clauses in. We say that this is the conceptual order because MySQL does not need to always follow the logical order when it's physically processing the query behind the scenes. However, MySQL will return a result that aligns with what we would expect from this logical query processing order. Okay, so MySQL's logical query processing order starts by evaluating the from clause first. Next we have the where clause, then we have the select clause, then group by, having, and finally order by gets evaluated last. Okay, a common analogy for thinking about this is by imagining that you are giving some instruction to a robot. And let's say you say to the robot, please get me a glass of milk and an apple from the refrigerator. This is how we would say it in English. However, the robot would need to rearrange the instruction into something like, go to the refrigerator, then open the refrigerator door, then get 1 glass of milk and 1 apple, take items back to the owner. Similar to this scenario, the logical processing of a query must first know which table is being queried before it can know which attributes are to be returned from the table. So this is why the from clause comes first in this conceptual order. The main implication of this conceptual processing order is where we can and cannot use column aliases. But before we cover that, I just want to mention that the MySQL conceptual order is a bit different from most other relational database management systems. Most other major databases, such as Oracle and SQL Server, have a conceptual order given on the right here. The main difference is that the select clause comes 5th, instead of 3rd, as we have in MySQL. Okay, so MySQL's conceptual order is important for understanding how queries are parsed. For example, we cannot refer to a column alias in the where clause, because column aliases are defined in the select clause, and the select clause gets evaluated after the where clause. So you can see here we have the where clause first, then we have select. So if we define a column alias in select, then we cannot reference it in the where clause. On the other hand, a column alias can be referred to in the order by clause, because the order by clause gets evaluated after the select clause. So we get the order by clause getting evaluated last. Now, in MySQL, we can actually refer to a column alias in the group by clause. And this is because the group by clause gets evaluated after the select clause. However, in just about every other database system, we cannot do this, because in most other databases, the group by clause gets evaluated before the select clause. To illustrate this further, let's now go for an example of a query. Okay, so here we have a table of products, and each product has a category and a price. Let's say we wanted to write a query that returns the average price for product categories that have an average price greater than $20. Exclude any products which have a category of unassigned. Order the query result by average price from highest to lowest. We can do this by writing the following query. So in MySQL's logical query processing order, we have the from clause gets evaluated first, then we have the where clause, so we filter the rows, then we have the select clause gets evaluated, next we have group by, then having, and finally we have the order by clause getting evaluated last. So if we try to refer to a column alias in the where clause, then we will get an error message. For example, so this query here gives the following error message, which is unknown column, product category, and where clause. If we look at the query, we can see that we have given the category column an alias of product category, and then we have tried to refer to this product category alias in the where clause. However, we cannot refer to a column alias in the where clause because the where clause gets evaluated conceptually after the select clause. However, in MySQL, we can refer to column aliases in either the group by clause or the having clause. For example, okay, so now we have referred to column aliases in both the group by clause and the having clause. We have group by product category, which was the alias for the category column, and then we have in the having clause average price greater than 20. So average price is the alias for the average aggregate function. This query works in MySQL because the group by and having clauses get evaluated after the select clause. However, in most other relational databases, this query will not work because select gets evaluated after group by and having. So this query here is quite specific to MySQL and won't work in the other major relational databases. And one other thing is that the order by clause always gets evaluated last in all the major SQL dialects. So we can always refer to column aliases in the order by clause regardless of the relational database system we are using. Alright, that's it for now. See you next time. Hello and welcome to the Group By Challenges. Alright, let's look at the first challenge. So for this challenge, you are to write a query to give the total number of employees in each department as given by the department ID column in the HCM.employees table. Alright, coming up next are the hints. So the hint for this challenge is to use the count aggregate function in the select clause. Also note that this challenge, as well as all the other challenges in this lecture, will require a group by clause. Okay, let's move to the second challenge. So for the second challenge, you are to write a query to give the average salary in each department as given by the department ID column in the employees table. Order the query result by average salary from highest to lowest. Alright, let's take a look at the hints. So the hint for this one is to include the average AVG aggregate function in the order by clause. Okay, let's move to the third challenge. So for this challenge, you are to write a query to give the total number of products on hand at each warehouse as given by the warehouse ID column in the OES.inventories table. Also, limit the result to only warehouses which have greater than 5,000 product items on hand. Also, I should mention that in the OES.inventories table, there is a column called quantity on hand, which gives the quantity of products on hand for a particular product at a particular warehouse. Coming up next are the hints. So use the sum aggregate function and also include a having clause in the query. Alright, let's now move to the fourth challenge. So for the fourth challenge, you are to write a query to answer the following question. What is the date of the most recent population count at each locality in the bird.Antarctic populations table? Coming up next are the hints. So for this one, you can use the max aggregate function. Okay, let's look at the fifth and final challenge. This challenge, you are to answer the question, what is the date of the most recent population count for each species at each locality in the bird.Antarctic populations table? And the hint for this one, you will need to group by more than one column. Alright, so have a go at doing those challenges, and in the next tutorial we'll be going through the solutions. Okay, welcome back everyone. So now we're going to go through the solutions to the group by challenges. And before doing the first challenge, I'm just going to select all data from the HCM.employees table. So let's do that. Okay, so in this table we have employees, and each employee belongs to a department as given by the department ID column. So for the first challenge, we were to answer the question, how many employees are there in each group? And we can do that with this following query here. So we have select department ID, and then we're going to use the count aggregate function to count up all the rows. So we're using count asterisk, and then I'm going to call this expression as employee count. We're selecting from the HCM.employees table, and we're grouping the data by the department ID column. So we're going to count up the rows within each department ID group. Alright, so let's now execute the query. So in the query result, we can see that we have 29 employees who are not assigned to any department, as given by the null here. And then we've got 6 employees in department ID 30, 25 employees in department ID 50, etc. And note that this count asterisk is going to actually count these nulls, whereas if we had actually specified the department ID column in the count function, then it would not have counted the nulls. So just to demonstrate that, I'm going to remove the asterisk, and then I'm going to type department ID, and so we'll just run this one. So now you can see we have an employee count of 0 for where the department ID is null, and that's because it's not counting up nulls as being actual values. But in this case we do want to count those employees who have not been assigned a department, and therefore I'm going to change it back to the asterisk. And we'll run that again. Okay, so that's giving us the result we want. Let's now move to the second challenge. And so for the second challenge, you were to return the average salary for each department, and you were to order these departments by average salary from highest to lowest. So similar to the previous challenge, we're going to be grouping by the department ID column, and that's because the question says we want to get the average salary in each department. So wherever you see the word each, think of group by. So each department, group by department, or in this case, department ID. So in the select clause, we have select department ID, comma, and then we're going to be using this time the average aggregate function. So that's just AVG. We pass in the column that we want to get the average for, which is the average salary. And then we're going to alias this expression to this AVG underscore salary. And then we're going to order the result by average salary in descending order. So from highest to lowest. So the order by clause actually happens after the select clause in the processing order. And this means that we can specify this alias, average salary, in the order by clause. Okay, so let's just click in here and execute it. And this gives us the result we wanted. So for example, for department ID 80, it has an average salary of $217,309. Note that we have quite a few decimal places here, and what we can do to tidy that up is to actually round the result. So I can go into this expression here and I can type the round function, open parenthesis. So we're going to round the average salary, and then I do a comma, and then for the second argument I'm just going to type, say, 1. So this will round it to 1 decimal place. Close parenthesis, so that's closing off the round function. Click here and then execute it. And this gives us a much tidier result as we've rounded the average salary to 1 decimal place. Alright, let's now move to the third challenge. So before doing the third challenge, let's just have a look at the oes.inventories table. So I'll just select all data from that table. So in the inventories table, we get the quantity on hand of each product at each warehouse. So for product ID 1 at warehouse ID 1, we've got a quantity on hand at this warehouse for this product of 112 units. And for product ID 1 again, but this time at warehouse ID 2, we've got a quantity on hand of 107 units. Okay, so for this challenge, you were to give the total number of products on hand at each warehouse, and then you were to limit the result to only warehouses which have greater than 5,000 product ID items on hand. So we can do that with this following query here. So if we look at the wording for the question, so it says total number of products on hand, this indicates that we want to sum up the quantity on hand column. So we're using the sum aggregate function, and then it says at each warehouse. So we want to group by warehouse, or in this case, warehouse ID. So our resulting query is select warehouse ID, sum, the quantity on hand attribute, and I'm aliasing this one to just total products on hand from oes.inventories, group by the warehouse ID, and then last of all, we're going to use the having clause to restrict the groups returned, and we're restricting the groups returned to only those warehouses which have greater than 5,000 product ID items on hand. So the having clause happens before the select clause, and this means that we need to repeat the sum function here. So we need to sum up the quantity on hand again. So we're saying where the sum of the quantity on hand is greater than 5,000. So let's just click in here and run the query. Okay, so this is the total number of products on hand at each warehouse for warehouses which have greater than 5,000 products on hand. Okay, so let's now move to the fourth challenge. So before doing the fourth challenge, let's have a look at the bird.antarctic populations table. So we'll just have a look at all the data in this table. So we use this one during the select distinct challenges, and this just gives us our population counts that were done at various localities for various species, and we also get the date that the population count for that species was completed. So for this challenge, you were to answer the question, and that was, what is the date for the most recent population count for each locality in the bird.antarctic populations table? So if we were to do this visually just by looking at the data in the table, say for Anvers Island, we can see we've got a few rows here, and then we'd look across and see which is the most recent date. So it looks like it would be the 18th of the 9th, 2020. So this would be the row that we would want to return for Anvers Island. And then we would do the same for the other localities. So how we would write that in the query is that this time we're going to be grouping by the locality column, as it says for each locality. So we group by locality. So we want to return the date for the most recent population count. So the date of count column gives the date on which the population count was conducted. And remember that later dates are greater dates. So we want to return the greatest date, i.e. the most recent date, for each locality. So in our select clause, we have select locality, and then we're using the max function to get the maximum value from the date of count. And in this case, I'm just calling this date of recent pop count, or population count. And click in the query, execute it. So now in the result, since we're grouping by the locality, we're going to get unique values for each locality returned. And we also get the date of the most recent population count at each locality. Okay, let's now move to the fifth challenge. So for the fifth challenge, we were to answer the question, what is the date of the most recent population count for each species at each locality in the bird.antarctic populations table? So looking at the wording of this question, we have for each species, and then we also have at each locality. So we have the word each twice, once for species and once for locality. And this means we're going to need to group by both the locality and the species ID columns. And it doesn't matter what order we put these in the group by clause, we'll still get the same result. And in this case, again, we're going to use that max date of count to get the date of the most recent population count. So let's just click in here and execute the query. Okay, so now we're grouping by both the locality and the species ID. This means that we may get duplicates for locality if more than one species has been counted at that locality. But if we combine both the locality and the species ID, then the combination of values will always be unique. So it's a bit like doing select distinct. But in this case, we're doing group by because we're also interested in using an aggregate function. So for example, the most recent population count for species ID 4 at South Georgia Island was done on the 20th of the 9th, 2020, and the most recent population count for species ID 2 at South Georgia Island was done on the 5th of November, 2020. Alright everyone, that's it for this lecture. I'll see you in the next one. Now we are going to look at the AND operator. So on the left here, we have a table of room details for rooms at a hotel. For each room number, we have a room style, which has whether it is a single or double bed, and we also have a column called window view that gives what type of scenic view each room has. So let's say we had been given the following task. Write a query to return only hotel rooms that have both a room style equal to single and a window view equal to ocean. So to do this, we use an AND operator in the where clause. Let's now look at the query. So when we use an AND operator, we are saying that both conditions must be true for the combination to be true. Otherwise, the answer is false and the row is not returned. So let's go through this table row by row to see which rows get returned by this query. So if we look across at room number 1, does it have a room style of single? Yes, it does. So that condition evaluates to true. And does room number 1 have a window view of ocean? Yes, that condition also evaluates to true. Both conditions evaluate to true, and therefore this row gets returned. Now let's look at room number 2. Does it have a room style of single? No, it does not. It has a room style of double. And if we look at the second condition, does it have a window view of ocean? Yes, it does. However, both conditions need to evaluate to true when using the AND operator in order for the row to be returned. And in this case, only one of the conditions is true. Therefore, the result of the AND operator is false and the row is not returned. Room number 3 is single and ocean. Both evaluate true, so this row is returned. Room number 4, the first condition evaluates to true, and the second condition evaluates to false. Therefore, the result is false and the row is not returned. And for room number 5, this row does not meet either of the conditions and therefore is not returned. So the end result is that 2 rows are returned, and these are rooms 1 and 3, and these are returned by the query. Now we're going to take a look at the OR operator. So again, we have our table of hotel rooms. So let's say that this time we had the following task. Write a query to return only hotel rooms that have a room style equal to single or a room view equal to ocean. So now we need to use an OR operator in the where clause. Let's take a look at the query. So when we use an OR operator, we are saying that at least one of the conditions needs to be true for the combination to evaluate to true. Otherwise the answer is false and the row is not returned. So let's go through this table row by row to see which rows get returned by this query. Looking at room number 1, does it have a room style equal to single? Yes. So the first condition is true. The second condition is also true. The result therefore is that this row is returned. Room number 2, is the room style single? No. So this condition gets evaluated false. However, for the second condition, is the window view ocean? Yes, it is. So the second condition evaluates to true. Therefore, the result is true and the row gets returned because at least one of the conditions has evaluated to true. So now we're looking at room number 3 and both conditions are true. So this row gets returned. So now we're looking at row number 4 and does it have a room style equal to single? Yes, it does. So this condition is true. Does it have an ocean window view? No, it does not. Instead, it has a mountain view. The second condition therefore evaluates to false. However, this does not matter because at least one of the conditions evaluated to true and therefore this row gets returned. And last of all, we have room number 5. So does room number 5 have a room style equal to single? No. Does room 5 have a window view equal to ocean? No. Therefore, both conditions evaluate to false. So room 5 will not be returned by this query because none of the conditions are true. So in summary, this query returns 4 rows and the only row not returned was for room number 5 because neither of the conditions was met. Now we will be looking at operator precedence. And I'll be going through an example where we use both the and or operators in the same query. Misunderstanding operator precedence is a common error people make when writing SQL. Okay, let's get started. Again, we have our hotel rooms table, and let's say we write the following query against this table. So this query is saying select all columns from the hotel rooms table where room style equals single or room style equals double and window view equals ocean. Given this table, how many rows will be returned by this query? You might want to pause the video and try and work this out. Okay, so the answer is that 4 rows are returned by this query, and these are the ones shown here in the red box. Now, if you thought that 3 rows would be returned, you are not alone. Most people tend to. But actually, you'll get 4 rows. Why is this? It is because of the AND operator, and the AND operator has precedence over the OR operator. In English, we are used to reading from left to right. So in this case, a person might read the query as asking for all rows with a room style of either single or double, and also with an ocean window view. However, this is not the case in SQL. Instead, the AND operator gets evaluated first. So this part here gets evaluated first. The 2 conditions on either side of the AND operator. So first, SQL is looking for all rows where the room style equals double and window view equals ocean. Then it does the OR condition, or where room style equals single. So the query is going to return all the rooms with a room style of single regardless of what the window view value is. And you can see that with room number 4, which has a room style of single, so this row gets returned even though it does not have a window ocean view. If we want to evaluate the OR operator before the AND operator, we can do this by putting parentheses around the conditions on either side of the OR operator. This is because parentheses have the highest level of precedence and therefore get evaluated first. So let's now look at that. Okay, so now we have put parentheses on either side of the OR operator. This therefore forces everything within the parentheses to get evaluated first, and therefore the OR gets evaluated before the AND. So how many rows will now be returned by this query? And the answer is 3 rows get returned. So now we are returning all the rooms that have a room style of single or double, and the room must have an ocean window view. Let's now look at the precedence level of various operators. So at the top of this chart we have parentheses, which have the highest precedence, and therefore what's in parentheses gets evaluated first. Then we have multiplication and division, followed by subtraction and addition. Then we have the NOT operator, then the AND operator, and last of all we have the OR operator, which has the lowest level of precedence and therefore gets evaluated last. Welcome back everyone. Now we are going to be covering the IN operator. Let's get straight into it. The IN operator can be used to check if a value is included in some specified list of values. The IN operator allows you to specify multiple values in the where clause. We can also specify a subquery after the IN operator. More on that later in the course. Okay, let's have a look at the basic syntax for the IN operator. So here in the syntax we have where, and then we specify a column, then we have the IN keyword, and then after the IN keyword, within parentheses, we specify each value in a comma delimited list. In other words, we want to return the rows from the table where the values in column 1 match one of the values we specified in the parentheses here. Okay, let's go through some real examples. So here we have a table called shipments, which has parts ordered from various suppliers. Let's say we wanted to write the following query. So we want to write a query to return all shipments from suppliers 101, 102, or 104. One way we can do this is we can write a series of OR operations against the supplier ID column. For example, now we have a where clause and we are only keeping rows where supplier ID equals 101 or supplier ID equals 102 or supplier ID equals 104. And we can see that we get one of the rows excluded from the query result, and that's supplier ID 103 gets removed. A quicker way to write the same query is to use the IN operator. For example, okay, so now we have in the where clause where supplier ID in, and then within parentheses we specify our values and we separate each value with a comma. Now if we were querying a character data type column, then we would need to enclose each value in single quotation marks. To show that, let's first return to show all rows from the table again. Okay, so let's say our new task is to write a query to return all shipments for part names brake drum and fuel filter. So we will add on a where clause and use the IN operator. Okay, so now we get 3 rows returned. And in this case we have where part name in, and then in parentheses we have the values but this time the values are enclosed in single quotation marks, and this is because the part name column is a character data type column. In this case, it is a variable character data type column. Okay, that's it for this lecture on the AND operator. See you in the next one. Okay, so it's time for some more challenges, and this time we'll be covering the logical operators. Okay, let's look at the first challenge. So for the first challenge, you are to write a query which selects employees from the hcm.employees table who live in either Seattle or Sydney. Next up is the hint for this challenge. So for this challenge, you can use the OR operator. Okay, let's now look at the next challenge. For the second challenge, you are to select employees who live in any of the following cities: Seattle, Sydney, Ascot, or Hillston. Coming up next is the hint. So for this one, you can use the IN operator. Okay, let's now go through the third challenge. Select employees from Sydney who have a salary greater than $200,000. Coming up is the hint. Use the AND operator. Okay, now time for the fourth challenge. So for the fourth challenge, you are to select employees who live in either Seattle or Sydney and were also hired on or after the 1st of January 2019. Okay, let's now take a look at the hint. So for this challenge, you'll need to use both the OR and the AND logical operator. And also remember about precedence, so you'll have to be mindful of precedence as well. Okay, let's now go through the fifth and final challenge. So for the last challenge, you are to select products from the OES.products table which do not have a product category ID of either 1, 2, or 5. Okay, so try writing query solutions for these 5 challenges, and in the next video, we will go through the solutions. Okay, welcome to the solutions to the logical operator challenges. So for the first challenge, we were to select all employees from either Seattle or Sydney. So in the query here, we just have select all columns from hcm.employees where city equals Seattle or city equals Sydney. So because we're using the OR logical operator, only one of these conditions needs to evaluate to true in order for the row to be returned. Okay, so we'll click in here and execute it. So these are all the employees from either Seattle or Sydney. Alright, let's move to the second challenge. So for the second challenge, you were to select all employees who live in one of the following cities: Seattle, Sydney, Ascot, or Hillston. So because we have quite a few conditions here, we can use the IN operator. And the IN operator essentially does a set of OR conditions. So in this case, we write where city in, and then within parentheses, we just specify all the values we want to search for. So in this case, we have the city names. Okay, so let's execute that query. So now we get 47 rows returned. So we have a couple more employees compared to the first challenge. So if we go along to city, we see we've got Seattle, Sydney, and down here we have one employee in Hillston and one in Ascot. And this is essentially doing the same as this, or the set of all conditions. But as you can see, this one's a bit more verbose to write. So we have to have city equals Seattle or city equals Sydney or etc. But that would give you the same result. Okay, so let's move to the third challenge. So for the third challenge, you were to select employees from Sydney who have a salary greater than $20,000. So because both these conditions need to be true, so they need to be employees who are both from Sydney and have a salary greater than $20,000, we need to use the AND logical operator. So we have where city equals Sydney and salary greater than $200,000. And the city column is a string, so I've put it in single quotation marks. Salary is a number, so no quotation marks around the number. Okay, so click in here, execute the query. So only 2 employees meet these 2 conditions, and they are Patricia and Daniel. So both these employees live in Sydney and earn greater than 200,000. Alright, let's move to the next challenge. So for the 4th challenge, you were to select employees who live in either Seattle or Sydney and were hired on or after January the 1st, 2019. So in this case here, we want to check if they are first of all in one of these 2 cities. So we have city equals Seattle or city equals Sydney. And we also want to make sure that they were hired on or after January 1st, 2019. So we have and hire date greater than or equal to 2019-01-01. So this is year, month, day. But remember the precedence with logical operators, and that's the and gets evaluated before the or condition. And in this case, we want the 2 conditions on either side of the or condition to be evaluated first. So we need to use parentheses to force the precedence. So everything within the parentheses gets evaluated first. So because parentheses has the highest level of precedence, this means that this part here will get evaluated first. So first of all, SQL is going to look at the conditions. Is the employee in Seattle or are they in Sydney? And if either of these conditions are true, then we move to the AND condition. So we're going to look at whether they were hired on or later than 2019 January the 1st. Okay, so let's click in here and execute the query. And we get 6 rows returned. Alright, let's move to the 5th and final challenge. Okay, so for the 5th challenge, you were to select products that are not in categories 1, 2, or 5. So we have select all columns from oes.products, where category ID not in, and then within parentheses we specify the values for the category IDs that we do not want, which are 1, 2, and 5. So click in here, execute it. So all these products have category IDs which are not 1, 2, or 5. And we could have also written this query like this. So we could have had where category ID does not equal 1 and category ID does not equal 2 and category ID does not equal 5. So obviously this takes a lot longer to write than if we did not in. Alright everyone, that's it for this lecture. See you in the next one. Welcome everyone to this lecture on inner joins. Let's get straight into an example. So here we have 2 tables. On the left, in orange color, we have a table of departments. And on the right, in blue, we have a table of employees. If we want to write a query to connect rows from both tables, we can do so by joining the tables. So let's show the query. Okay, so in this query, we're using an inner join, and this is only going to connect matching rows. In the query syntax, we have select star from departments, then we have the keywords inner join, and then we write the name of the table we want to join to, which in this case is called employees. And then we have the keyword on, and then we have departments.deptID equals employees.deptID. What this means is that we are going to only join rows which have the same department ID, deptID, in both tables. This query returns the following result. In the query result, we can see that we have 2 rows for the accounting department. And if we look up top at the departments table, we can see that the accounting department has a department ID of 101. And if we look across at employees, we can see that we have 2 employees, Rose and Ben, who are assigned to department 101. The marketing department, which is department ID 102, has 1 matching employee for employee Andrew, and the sales department 103 also has 1 employee for Claire. However, notice that department ID 104, the IT department, currently has no matching rows in the employees table. In other words, there are currently no employees in the IT department. Since we're using an inner join, this means that only matched rows between the tables are returned in the query result. Therefore, the IT department gets discarded from the query result since it has no matching rows in the employees table. Going back to the query, the join's matching condition is specified in the on clause. In this case, we are matching departments and employees which have the same value for dept ID. Since we are now selecting from multiple tables, we need to let SQL know which table each column is coming from, and we are doing that by having the table name as a prefix to the column name. We are asking SQL to get the dept ID from the departments table and match it to the dept ID from the employees table. Typically, instead of writing select star in the select clause, we will specify a subset of columns from the tables. For example, so now in this example, we are selecting the dept ID, which we are getting from the departments table, and we are also getting the dept name from the departments table, and then we're selecting a couple of columns from the employees table, the emp ID and the first name. To make this query a bit quicker to write, it is common for people to use aliases for the table names. Let's show that. Now in the from clause, we have from departments D, so we are aliasing the departments table to the letter D, and then we have the keywords inner join, and then we have employees E. So we are also aliasing the employees table, and we are aliasing it to the letter E. This now means that we can just write the alias D and E when referencing columns, and SQL will know which table we mean. For example, in the select clause, we have d.deptID, and SQL now knows to get the department ID column from the departments table, as we have aliased it to the letter D. And we are now also using table aliases in the on clause. Another way we can shorten this query is by removing the inner keyword. So the inner keyword is optional, which means we can remove it and we will still get the same result. For example, so now we just have the keyword join, and this will default to doing an inner join. Welcome everyone to this lecture where we will be covering both the left outer join and the right outer join. Okay, let's get started. In this query, we are selecting a couple of columns from each of the tables, and in the from clause, we have the keywords left outer join. And what this is going to do is it is going to return all rows from the left-hand side table, even if there are no matches in the right table. This query gives the following result. So in this query, the departments table is the left table, as it has been specified first, and we can see that departments is on the left-hand side of the left outer join keywords. The employees table is the right table. So we are joining the tables based on the department ID column, and notice that the IT department, department ID 104, has no matches in the employees table. However, because a left join preserves all rows from the left table, this means that the IT department has been included in our query result down here, even though it does not have any matches. Also notice that nulls are given as placeholders in the query result for unmatched rows on the right side. For example, in the query result, the IT department is given nulls for the employee table attributes, i.e. emp ID and first name. So currently we have both tables on the same line in the from clause. However, we don't need to write it this way. For example, we could put them on different lines. So this is still the exact same query, and departments is still the left table as it is specified first. Also, the outer keyword is optional, so we can remove it and we will still get the same result. So now we just have left join instead of left outer join, and this means the same thing. Okay, let's go back to the original query formatting. So let's rewrite this query, but instead we will write it using a right outer join. So a right outer join is where we preserve all rows from the right table. So if we wanted to get the same result as given here, but as a right join, we just need to change the order of tables in the from clause to specify the employees table first. So let's do that. So this query gives the same result as before, because we have now changed the order of the tables. So now employees is our left table, and departments is our right table. Because we are using a right outer join, all rows from the right table are going to be preserved, even if they have no matches in the other table. Departments is our right table, because it has been specified after the employees table. So the query includes the IT department, the same as before. Most languages are written from left to right, so most people are used to thinking in these terms as well. Therefore, where possible, I recommend ordering tables in a way that uses left outer joins rather than right outer joins, as most people will find the left outer join more intuitive to visualize. Welcome everyone to this lecture on full outer joins. Okay, let's get started. Here we have a table of students and we have a table of test scores. We can join these two tables on the student ID column in each table. However, notice that not all students have a test score. For example, Hannah, who has a student ID of 3, does not have a row in the test scores table. Also notice that student ID 5 appears in the test scores table. However, there is no student ID 5 in the students table. If we were to do an inner join, we would only get matched rows returned. Therefore, both student ID 3 and 5 would be excluded from the query result. If we want to include all rows, including unmatched rows, from either table, then we can do so by using a full outer join. Let's do that. So in this query, we have the keywords full outer join. And we are doing a full outer join between the students table, which we have aliased to the letter S, and the test scores table, which we have aliased to the letters TS. And we are joining on the student ID from each table. Since we are using a full outer join, we get all rows, including unmatched rows, in our query result. If we look at the first row here, this is the unmatched row that came from the test scores table. Therefore, it has nulls as placeholders for the attributes we are getting from the students table. Notice that we have included the student ID column from both tables in the select clause, and we have aliased the student ID from the test scores table to name it TS student ID. Since we have done this, we can see that the unmatched row coming from the test scores table is for student ID number 5. The next few rows shown are the matched rows that get joined, and the last row is an unmatched row, but this time coming from the students table. Therefore, we have nulls as placeholders for the attributes coming from the other table, i.e. the test scores table. Recall that the ordering of rows in the query result cannot be guaranteed to be in a particular order unless we use an order by clause. So in this case, we could get the rows returned in any order. The outer keyword is optional, so we can remove it and we will still get the same result. As an aside, it is relatively uncommon to need to do a full join in a properly designed database. For instance, in a well-designed database, there would be a foreign key constraint on the student ID column in the test scores table. This would reference back to the student ID column in the students table. This would have the effect of preventing student IDs from being inserted into the test scores table that do not exist in the students table. This would mean that student ID 5 would not have been allowed to be inserted into the test scores table because it does not exist in the students table. We will be covering foreign key constraints in detail later on in the course. Hello and welcome to the lecture on integrity constraints. Let's get straight into it. Data integrity refers to the accuracy and consistency of data. In relational databases, we can enforce data integrity by adding constraints on columns in a table. So the common types of data integrity constraints are primary keys, foreign keys, not null, unique, and check constraints. And in this lecture, we are going to be focusing on the first two, primary keys and foreign keys. Let's first go through the primary key constraint. A primary key constraint is placed on a column or a set of columns, and this constraint ensures that the values in the primary key column or columns are both unique and not null. Both of these conditions need to be met. A single table might have many potential candidate keys, but only one candidate key is selected to have a primary key constraint placed on it. Note that a candidate key is essentially a column or combination of columns which have unique values. A table can only have one primary key constraint placed on it. Alright, let's have a look at a quick example. So here we have a table of students, and we have student ID, first name, and last name. The student ID column has all unique non-null values. Therefore, one option is that we could place the primary key constraint on this column. And if we look at the other columns, such as the first name column, we can see that we have two students with the same first name, Amy. And so this column is not a candidate key. And we've got a similar thing going on for the last name column, as we have two students with the same last name, which is Reed. So because of these duplicates, we couldn't place a primary key on either first name or last name. But what we could do is we could actually place the primary key on both the first name and last name in what's called a composite primary key. And this is because we have unique combinations of both first name and last name. However, this would be a bad idea, and this is because in the future it is possible that we could get two students who have the same first name and last name, and if this happened, then we wouldn't be able to insert the student into the table if there already was another student with the same full name. So in this case, it is actually best practice to put the primary key constraint on the student ID column, as this column can always be used to uniquely identify each student. Alright, let's take a look at another example, but this time in MySQL Workbench. Okay, so we've got the integrity constraints demo open in MySQL Workbench. And in the first query here, I'm just going to select all rows from the HCM.departments table. So execute that. So in this table, we have the department ID, department name, and location ID. And in this next query here, I'm counting up the total number of rows. So I'm using count star as total row count. And I'm also getting a count of the distinct department ID values. So I've got count distinct department ID, and I'm calling this expression distinct row count. So just click in the query and execute that one. So you can see we have a total row count of 27, and we also have a distinct row count of 27. And because the total row count is equal to the distinct row count, this means that there are no duplicates in the department ID column. and this is actually enforced by a primary key constraint on the department ID column in this departments table. And we can see that if we go to HCM tables, look at the departments table, columns, click on department ID, and if we look down here for department ID, we can actually see that we have this PK on the end here, and that stands for primary key. So our department ID is our primary key column. So it will always have unique non-null values. Alright, so another way that we can see which constraints are on a table is by using the information schema system views. And recall that the information schema gives us metadata information about various objects in our database. So to show that, let's just scroll down a bit. Okay, so we're going to be joining the information schema.table constraints to the information schema.key column usage. And tables constraints returns one row for each table constraint, and key column usage shows which key columns have constraints on them. So we'll scroll down a bit more. Okay, so this is the query here, and this particular query will give us the constraints on the HCM.departments table. So let's just run the query first, and then we'll have a talk about it. Okay, so we can see that we actually have two constraints on the departments table. We have a primary key constraint on the department ID column, and we have what's called a foreign key constraint on the location ID column. We'll talk about foreign keys in just a moment, but first I'll just mention about this query, and that is that we're selecting the first few columns from the table constraints, and then we're joining on to this key column usage, and we need to join these two on multiple columns, and we're just filtering to the departments table in the HCM schema. Don't worry if this query seems a bit confusing. I just wanted to show you that there's more than one way to get the constraints on a table. Alright, let's now switch back to the presentation where we will cover foreign key constraints. Okay, so here we have a table of departments, and there is a primary key constraint on the department ID column in this table. As discussed, this ensures that values inserted into this column need to be both unique and not null. For instance, we already have a department ID value of 104. So if someone tried to insert a new row with a department ID of 104, then they would get an error message saying something like duplicate values are not allowed. Okay, so let's now look at another table, and this time our table of employees. So in this table, the primary key is the employee ID column. But this table also has another constraint on it, and that is called a foreign key constraint, and it is placed on the department ID column in this table. So this particular foreign key references back to the primary key in the departments table. The foreign key constraint on the department ID column in the employees table ensures that the values inserted into the employees table's department ID must match existing values in the departments table department ID. Okay, so there's a lot going on there, but basically what this means is that, for instance, if someone tried to insert a row into the employees table and they gave a department ID value of 105, then they would get an error message because there is no department ID 105 in the departments table. If they wanted to insert a new employee for department ID 105, they would first have to update the departments table and add the new 105 department in. So in other words, you cannot assign an employee to a department that does not exist in the departments table. Okay, so notice that the foreign key does not prevent nulls from being inserted. So in this case, we have an employee named Gloria who has a null for the department ID. Although it has not been used here, often a foreign key constraint column will also have a not null constraint applied to it to prevent nulls from being inserted. The primary key to foreign key relationship is a foundational concept in relational databases. They show how tables can be joined together. In this case, we can join departments to the employees table based on the department ID column. So if we did an inner join with the data shown here, we would get 5 rows returned. Another thing to mention is that it is common to hear the terminology parent table and child table. In this case, the departments table is the parent table with respect to the employees table, which is our child table. If you think about the analogy that a parent can have 0 or more children, so here we would say that a department could have 0 or more employees. Let's now take a look at what these two tables would look like in an entity relationship diagram. Most database entity relationship diagrams will look like this, except with many more tables and also some more metadata information. So the first row in each box indicates the table name. The rows beneath are the column names in the table. In this diagram, the underlined column name indicates that it is the primary key. And notice the crow's feet on the department ID column in the employees table. This indicates that it has a foreign key and is therefore on the many side of the relationship. So we have a one-to-many relationship between departments and employees, as indicated by the one bar on one side and the crow's feet for the many side. By looking at this diagram, straight away we can see that the two tables can be joined based on the department ID column. Alright, let's now summarize the key points to remember when it comes to foreign keys. Foreign keys are used to enforce referential integrity between tables. In a one-to-many relationship, the foreign key constraint is placed on the child table, which is the many side of the relationship. The values of a foreign key column uniquely identify a row of another table or the same table. When a foreign key references the same table, this is called a self-referencing foreign key. However, in most cases, the foreign key usually refers to the primary key in another table. A column with a foreign key on it will only have values that first exist in the primary key column of the table that it references. The caveat to this point is that the foreign key column can also have nulls. However, this can be mitigated separately by placing a not null constraint on the column as well if required. One more thing to note is that it is possible to have a foreign key which references a column which has a unique constraint placed on it, rather than a primary key. A unique constraint is similar to a primary key in that it constrains a column to have unique values. However, one of the main differences between a primary key constraint and a unique constraint is that a unique constraint allows a null. Also, a table can only have one primary key, whereas it can have multiple unique constraints on it. With that being said, the vast majority of foreign keys that you will encounter in the real world will reference back to a primary key. Alright, so that's it for this lecture. We've covered a lot of material and I hope you've found this informative. Hello and welcome to the lecture on many-to-many relationships. In this lecture, we are going to look at how many-to-many relationships are modeled in relational databases. We will also look at how these look in an entity relationship diagram. Okay, let's get started. A many-to-many relationship exists between two entities when an instance of entity A can potentially be associated with many instances of entity B. In addition, a single instance of entity B can potentially be associated with many instances of entity A. Therefore, we cannot say that one entity is the parent and the other entity is the child. An example of a many-to-many relationship is between the two entities doctors and patients. Each doctor sees many patients, and each patient may see many different doctors. The correct way to model a many-to-many relationship is to create an associative table. This is sometimes referred to as a junction table or a linking table. Let's now take a look at an example. So keeping with our doctor-patient example, to model the many-to-many relationship between these two entities, we create an associative table, which is this table in the middle here called doctor-patients. This associative table has unique combinations of the doctor ID and the patient ID, which we enforce using a composite primary key. The primary key is a composite one because it includes both doctor ID and patient ID. Doctor ID on its own does not have unique values, but the combination of both doctor ID and patient ID is guaranteed to be unique because of the composite primary key constraint. We also have two foreign keys on this table. These foreign keys establish the relationships back to each of the parent tables, with the parent tables being the doctors table and the patients table. Notice that we no longer have a direct relationship between the doctors and the patients table. Instead, we have two one-to-many relationships enforced by each of the foreign keys in the associative table. On one side, we have a one-to-many relationship between doctors and doctor patients. On the other side, we have another one-to-many relationship between patients and the doctor patients table. If we take a closer look at the table, we can see that Dr. Jackson has a doc ID of 1001, and if we look at the linking table, we can see he's got two patients, patient IDs 1 and 2. Moving across to the patients table, we can see that these patients are Perkins and Reeves. However, the patient with the last name Reeves, patient ID 2, also has seen Dr. ID 102 and 103, who are Drs. Anderson and Dr. Robbins. To summarize, we can determine that the table in the middle is an associative table because it has a composite primary key, and each of the columns that make up the composite primary key are also foreign keys. Let's now take a look at what this would look like in an entity relationship diagram. So in this diagram, the underlined columns are the primary keys. So for the table in the middle, Dr. Patients, we have the composite primary key, which includes both Dr. ID and patient ID. The table has two foreign keys, as indicated by the crow's feet on each column in the associative table, and these reference back to the respective parent tables. Alright, let's now take a look at the entity relationship diagram for the sample DB database. This file is attached as a resource link to this video. So I'm just going to go and open up that PDF now. Okay, so here we have the tables in the sample DB database, represented in an entity relationship diagram. Okay, so the first thing I should note is that this diagram does not include the bird schema. It only has the tables in the HCM schema and the OES schema. So these tables up here are for HCM, and down here are the OES tables. So there are a couple of associative tables in the OES schema. One of them is the order items table. So let's make this a little bit bigger. So in the order items table, this has a composite primary key, which is the combination of the order ID and the product ID columns. So we have PK next to both these columns. We also have FK next to each column. So these are the foreign keys. So we have one foreign key, which is on the order ID column, which references back to the orders table. So we have a one-to-many relationship between orders and order items. The other foreign key, if we trace back the connecting line, references back to the products table. We actually have connecting lines which overlap, which makes it a little bit confusing to read the diagram. But in this case, we are looking for where it has crow's feet on one end and the vertical bar on the other. And in this database, the column names also match. So we've got product ID to product ID. So we can use the order items table to join the orders table to the products table, as the order items table has both order ID and product ID. Another associative table in this schema is the inventories table. So this table has a composite primary key which consists of both the product ID and the warehouse ID. Product ID references back to the products table, and warehouse ID references back to the warehouses table. So the inventories table can be used to support the many-to-many relationship between products and warehouses. You can use this entity relationship diagram to see how the different tables are related to each other when doing any of the course challenges which involve using joins. Hello everyone, and welcome to the join challenges. Okay, let's go straight to the first challenge. So for the first challenge, you are to write a query to return the following attributes for employees who belong to a department: employee ID, first name, last name, salary, and the department name. Coming up next are the hints. The hints for this one are get department name from the HCM.departments table. Get all other attributes from the HCM.employees table. Use an inner join between the two tables. This is because you are only to include employees who belong to a department. Alright, let's now move to the second challenge. So for this challenge, you are to write a query to return the following attributes for all employees, including employees who do not belong to a department: employee ID, first name, last name, salary, and department name. Coming up next is the hint. So the solution for this challenge will be similar to the first challenge, except this time you'll need to use an outer join. Alright, let's now move to the third challenge. So for this challenge, you are to write a query to return the total number of employees in each department. Include the department name in the query result. Also include employees who have not been assigned to a department. Coming up next is the hint. You will need to use an outer join as well as a group by clause for this query. Okay, so have a go at doing those few challenges, and in the next video we'll be going through the solutions. Alright, welcome back. So now we're going to go through the solutions to the join challenges. And the first challenge, you were to return employee details for employees who belonged to a department. So we only want employees who actually belong to a department. So we want matches between the employees table and the department table. So we're going to be using an inner join to do that. So if we look first at the from clause, we have from HCM.employees, and I'm just aliasing this to the letter E. And then we've got inner join HCM.departments, and I'm aliasing the departments table to the letter D. Then we're joining these two tables based on the department ID. So then we have the keyword on, and then I'm saying D.department ID. So this is the departments table department ID column is equal to E.department ID. So this is the employees table department ID as we alias the employees table to the letter E. And if we look at the select clause, we're getting most of our columns from the employees table. So we have E.employee ID, comma, E.firstname, comma, etc. But if we look at the last column, we're getting the last column from the departments table. So only the department name existed in the departments table. So therefore I've got D.department name. Alright, so let's just click in the query and execute it. Okay, so we get 78 rows returned. So we can see all the employees and their department name that they belong to. And actually there's 107 employees in the table, but only 78 of these have a match in the departments table. Alright, let's now move to the second challenge. So for the second challenge, you were to return employee details for all employees, including employees who do not belong to a department. So since we want all employees, we're going to be using an outer join. And in this case, I'm using a left outer join. And to get all employees, this means I need to specify the employees table on the left-hand side. So I need to specify employees first. So I've got from HCM.employees, E, left outer join HCM.departments, D. So this is very similar to the previous query, except instead of doing an inner join, we're doing a left outer join, and we're putting the employees table on the left-hand side to ensure that we get all employees returned, even if they don't have a match in the departments table. So let's just execute the query. Okay, so now we get all employees returned, so we get 107 rows returned. And if we scroll down a bit to near the bottom, we can see that we get the employees returned who do not belong to a department. So ones like Olivia Grant, Richie Johnson, etc., they all have null for the department name column. And another way we could have written this query is by using a write outer join. So let's just take a look at that. Okay, so now we're doing write outer join, but because we want to get all employees, we now need to specify the employees table on the right hand side. So a write outer join will return all rows from the right hand table. So all we've done is we've switched around the department and employees table to make sure that the employees table is specified second. Okay, so if I click in there and execute it, we'll get the same result as we got before when doing a left outer join where we specified employees first. Okay, let's move to the next challenge. So for this challenge, you were to return the total number of employees in each department, and you were to include the department name in the result. Also, you were to include employees who have not been assigned to a department. So this last condition here, include all employees, even if they haven't been assigned a department, indicates we need to do an outer join. So I'm doing a left outer join and specifying the employees table on the left hand side. Again, we're joining the employees table to the departments table based on the department ID column in each of these tables. And after we have the from clause, we're then going to be grouping the data. So in this case, I'm grouping the data based on the department name column in the departments table. So we have d.department name as I alias the departments table to the letter D. And since we group by department name, we put department name in the select clause, and we're also using the count aggregate function to count the number of employees in each department. So we're getting the count of the rows, and we're grouping those rows based on the department name column. And I'm aliasing this expression to employee underscore count. Alright, so I'll just click in here and execute the query. And in the result, we can see that we have 29 employees who do not belong to any department. So we get a null. 6 employees in the purchasing department, 25 in shipping, 5 in IT, etc. And this query here is a bit similar to a challenge we did in the group by challenges, but this time we get a bit more of a meaningful result as we actually have the department name rather than just the department ID. But to get that, we had to do a join. Alright everyone, that's it for this lecture. See you in the next one. Hello and welcome back. In this lecture, we will be covering composite joins. A composite join is where we need to join tables that are related based on multiple columns. Okay, let's get started. So in this example, we have a table of cities and we have a table of stores. In the cities table, we have the population of each city, the name of each city, and the country. And note that we have 2 cities which have the same name. We have Melbourne in the USA and Melbourne in Australia. Therefore, we cannot use the city attribute by itself to uniquely identify each row. Instead, we need to use both the city and the country columns to uniquely identify each row in the cities table. Looking across at the stores table, each row is uniquely identified by the store ID column. And we have the floor size of each store in square meters in the area square meter column. And we have the city and country which each store is located in. So store 1 is in Melbourne, USA, stores 2 and 3 are in Melbourne, Australia, and store 4 is in Sydney, Australia. In order to correctly join these 2 tables together, we need to join on both the city and country columns. However, before we go through this, I want to show you what happens if we join the tables based on only one column. So let's show that. In this statement, we are inner joining the cities and stores on only the city attribute. Notice that in the select clause, we have included the country column from both tables, with the country column from the stores table being aliased to store country. Okay, let's go through each of the rows that will get matched when we do this join. So Melbourne, USA gets joined to Melbourne for store ID 1. Melbourne, USA gets joined to Melbourne for store ID 2. However, notice that store ID 2 is actually in Melbourne, Australia, not Melbourne, USA. Therefore, it is incorrect to join these two rows. And we can see that the country and the store country for this matched row have different values. Next we have Melbourne, USA joined to store ID 3. This is also an incorrect match as the countries are different. Then we move on to the city Melbourne, Australia. Melbourne, Australia gets joined to Melbourne for store ID 1. So again, this is incorrect because store ID 1 is in the USA. Then we have Melbourne, Australia joined to Melbourne for store ID 2. Then Melbourne, Australia joined to Melbourne for store ID 3. And finally we have Sydney, Australia joined to Sydney for store ID 4. This join has given us an incorrect result, as the query result includes rows that should not have been joined because they referred to different countries. In this case, if we want to get the correct result, then we need to join on both the city and country columns. Let's look at the correct query syntax. So notice now in the on clause, we are joining on both city and country. So we have on c.city equals s.city for the first condition, and then we have the AND operator, and then in the second condition we have c.country equals s.country. So both this condition and this condition need to be met in order for a row to get joined. The reason we need to do this is because in the cities table, the city attribute does not have unique values, as we have two cities with the same name. Also, in the stores table, city is not unique either. This means that we get a many-to-many relationship occurring when we join on just the city alone. To correctly do a join, we need to always join on a key. There are different types of key. However, here I'm defining a key as a column which has unique values, or a set of columns which has unique combinations of values. So the key in the cities table is the combination of city and country, as these have unique combinations of values. In the stores table, the only key we have is the store ID column. Notice that in the stores table, even if we combine the city and country columns, they are not unique. This is because we have two stores, store IDs 2 and 3, in the same Australian city. However, we can still use these attributes to join to the cities table because city and country combined do form a key in the cities table. As long as at least one of the tables involved in the join has a key, then we can use this key to join on to the other table. To summarize, I like to remember the saying, the key to a good join is to join on a key. Okay. Let's go through and show which rows get matched when we join on both city and country. Melbourne, USA gets joined to store 1 as store 1 is also in Melbourne, USA. Then we get Melbourne, Australia gets joined to Melbourne, Australia for store 2 and also for store ID 3. And then we get Sydney, Australia joined to Sydney, Australia for store ID 4. For complete illustration, let's include the city column from the stores table in the query. We can now see that we get the correct result because both the city and country values from each of the two tables match. Hello and welcome back. So far we have only been joining two tables together. In this lecture, we are going to see how to join more than two tables. These are also referred to as multi-join queries. Okay, let's get straight into it. Here we have three tables: doctors, doctor patients, and patients. First note that there is no direct relationship between the doctors table on the left and the patients table on the right. However, we have what's called an association table, which is this table in the middle called doctor patients. This association table can be used to link the doctors table to the patients table. The doctor patients association table gives all the unique combinations of doc ID and patient ID. Therefore, the key in this table is these two attributes combined. An association table is also known as a linking table, and it is used to model many-to-many relationships in relational databases. In this case, we have a many-to-many relationship between doctors and patients, as one doctor can see many patients, and one patient can see many different doctors. So our goal is to join these three tables together in order to get the doctors and patients they see. We can do that by writing the following query. So first we are joining the doctors table to the doctor patients table. This is followed by another inner join where we are joining to the patients table. When we have multiple joins in a query, then SQL evaluates the joins conceptually from left to right, or as it is written here, from top to bottom. The result of the first join is used as the left table input to the next join. So let's look at the first join. So we are joining doctors to doctor patients on the doc ID, and this gives the following conceptual result. This virtual result is then joined to the patients table. So we are inner joining on patients, and we are joining on the association table's patient ID, which is this dp.patientid, to the patients table patient ID. This gives the following result. So now we have each doctor's ID and last name, as well as each of the patients that they see. And we can see from this result that the patient with the last name Adams, a patient ID 104, has seen both Dr. Jackson and Dr. Naidu. Okay, let's just show the tables again. So let's take a new scenario. Let's say that a new doctor called Dr. Harford has just been hired. Let's add this doctor to the doctors table. So currently, Dr. Harford has not seen any patients. If we look at the same query as before, and if we run this query, then we will get the following result. This query is doing two inner joins, which means that Dr. Harford will get discarded from the query result as he has not been matched to any patients in the doctor patients table. If we want to include all doctors, including ones that don't have any patients, then you might be thinking that we just need to change the first inner join to a left outer join. Since the doctors table is the left table, we should get all doctors returned, right? Actually, no we don't. Instead, we get the same result as before. So again, Dr. Harford has been discarded from the query result. This has happened because the inner join that followed the left outer join has effectively negated the outer part. To understand this better, let's look at the conceptual output of the first join. The first join gives a conceptual result, which includes Dr. Harford, as we are doing a left outer join. Notice though that this produced a null as a placeholder for the patient ID. This conceptual result is then inner joined to the patient's table on the patient ID. It is at this point that Dr. Harford gets discarded from the final result, because of course this null is not joined to the patient's table. The final result is therefore the same as if we had used two inner joins. One way that we can address this problem is by making the second join also a left outer join, so that we have two left outer joins. For example, now we have two left outer joins and Dr. Harford is included in the query result. Welcome back everyone. In this video we are going to look at predicate placement. So recall that a predicate in SQL is a condition that evaluates to either true, false or null. When we have a query that has a join in it, then we can place a predicate in either the on clause, or we can put the predicate in a where clause. If we are using an inner join, the predicate placement does not matter. It will return the same result regardless of whether we place the predicate in the on clause or in the where clause. However, if we are using an outer join, such as a left outer join, then we will potentially get a different result depending on which clause we place the predicate in. Okay, let's go through some examples. So here we have two tables, a table of suppliers shown on the left and a table of products on the right. So these are the various products produced by the suppliers. Notice that we have the country that each supplier is located in. We have a few suppliers from India and we have one supplier from Germany. Also notice that the supplier Ace Corporation, which has a supplier ID of 2, does not have any products in the products table. So it is not supplying any products. Okay, so let's say we wanted to write a query which did the following. Return suppliers from India and the products they supply, i.e. only return Indian suppliers that are supplying products. We can return this result by writing the following query. So we are using an inner join, so this will only return matched rows. This means we only return suppliers that are supplying products. And then we have an additional filter, which is the where clause, where supplier's country equals India. This gives the following result. So notice that Ace Corporation is discarded from the query result when we did the inner join, as they have no products. Also notice that IT Solutions, which is supplier ID 4, has a matching row in the products table. However, this row gets discarded in the where clause, as we are only keeping rows where country equals India and IT Solutions is from Germany. So this gives us a few rows in our query result, 2 products from ABC Limited and one from XYZ Supplies. Another way of writing this query is to put the predicate in the on clause. Let's look at how we can do that. So again, we are joining on the supplier ID columns, but now instead of a where clause, we have the AND operator, then we have our second predicate. And that is supplier's country equals India. This produces the same result as when we put the predicate in the where clause. However, this is only true for inner joins. If we were using an outer join, then we would get a different result depending on where we specified the predicate. Okay, so let's go through predicate placement but this time using a left outer join. Let's say we want to do the following. Return suppliers from India and the products they supply, including suppliers from India that are not supplying any products. So we try writing the following query. We're using a left outer join. Suppliers is our left table, which means our query result will include all suppliers, even if they don't have products. And we have placed the predicate country equals India in the where clause. This gives us the following result. As expected, we get all Indian suppliers returned, so that includes Ace Corporation. Since Ace Corporation does not have any matching rows in the products table, it gets given nulls for the products table columns. Okay, let's try removing the where clause and instead place the predicate in the on clause using the AND operator. So at first, you might think that this will return the same result as before. However, this is not the case. Instead, this query returns the following. So notice that we get IT solutions included in the query result, even though they are from Germany. So we have two predicates in the on clause. The first one is supplier ID equals supplier ID, and the second one is country equals India. All predicates in the on clause serve a matching purpose. However, since we are using a left outer join, the query result will include all suppliers, even those that don't get matched. Ace Corporation is included, even though it does not have a match. In addition, IT Solutions is included, even though it does not have a match. Now, IT Solutions does have a matching product in the products table, as we can see here. However, it needs to meet both conditions in the on clause to be treated as a match. And of course, IT Solutions fails the second condition, which is country equals India. But the German supplier, IT Solutions, still gets included in the query result because we are including all suppliers, but it will have nulls for the columns coming from the products table. In this case, the predicate country equals India is not used as a filter. Hello and welcome back. In this lecture, we are going to be looking at self-referencing joins. A self-referencing join is also known as a self-join, and it is where a table is joined to itself. Self-referencing joins are useful for querying hierarchical data or comparing rows within the same table. Okay, let's get started. Here we have a table of employees. Each employee is uniquely identified by their respective employee ID. Notice also that we have a column called Manager ID, and this is actually the employee ID for each employee's manager. So we have a self-referencing relationship between employee ID and manager ID. For instance, James has a manager ID of 1. This means that James is managed by employee ID 1, and we can see that employee ID 1 is Judy. Judy is the CEO, so this means that James reports directly to the CEO. Amanda also reports to Judy. And then we have Bob and Henry, who both have a manager ID of 2, so they report to James, who we can see is the sales manager. Let's join this table to itself so that we can see the job title and the name of each employee's manager. In the from clause of this query, we have from employees E, inner join employees E2. So we are joining the employees table to itself, and we are aliasing the first instance of the table to the letter E, and the second instance of the employees table gets aliased to E2. Then in the on clause, we are matching rows where e.manager_id is equal to e2.employee_id. In effect, this means that attributes we select from the second instance of the employees table are going to be the manager details. Therefore, in the select list, we have aliased e2.firstname as the manager name and e2.jobtitle as manager title. This query gives the following result. To make the join easier to visualize, I'm just going to reorder the columns in the first table instance shown up top so that we have manager ID next to the second table's employee ID. So now it is easier to see that both James and Amanda have a manager ID of 1, so they get joined to employee ID 1, who is Judy, in the second table. And Bob and Henry have a manager ID of 2, so they get joined to employee ID 2, who is James, in the second table. However, notice that Judy, the CEO, is not included in the query result. Judy has a null for manager ID, therefore there is no match to the second table's employee ID, since Judy has no manager. Since we are using an inner join, we only get matched rows returned. If we want to include Judy in the query result, then we can do so by using an outer join. For example, so now we are getting Judy returned in the query result as we are using our left outer join, and this will preserve all rows from the left table, which is employees E. Hello and welcome back. In this lecture we are going to be looking at cross joins. Let's get straight into it. Here we have two tables, one for stores and one for products. Notice that these two tables have no link between them. In other words, there is no column or set of columns we can join the two tables on. However, we can still do a cross join between the tables. A cross join will join each row in a table to all the rows in the other table. To cross join the stores table with the products table, we can write the following query. In the from clause, we have from stores S cross join products P. And in the select clause, we are selecting all columns from both tables. This query gives the following result. The New York store gets joined to every row in the products table, and the London store gets joined to every row in the products table. So the query result has all combinations of rows between the two tables. A cross join is also called a Cartesian product, as it performs a cross product between two tables. We have 2 rows in the stores table and 3 rows in the products table. 2 times 3 is 6, so we get 6 rows when we do a cross join between these two tables. Another way of writing a cross join query is to simply use a comma between the tables. For example, so now we have in the from clause, from stores S, comma, products P. And this will also do a cross join. A cross join is a very simple join as we don't need to specify an on clause. However, there are not many situations where you will need to use this type of join. Hello everyone and welcome to the Advanced Join Challenges. Okay, let's look at the first challenge. So for this challenge, you are to write a query to return employee details for all employees, as well as the first and last name of each employee's manager. So include the following columns: employee ID, first name, last name, manager first name, and manager last name. So manager first name will be an alias for first name, and manager last name will be an alias for last name. Alright, so coming up are the hints. So the hints are that you'll want to join the employees table onto itself. So in other words, you want to do a self join by joining the manager ID to employee ID. So you'll want to join manager ID from one instance of the employees table to the employee ID of another instance of the same employees table. Also, you'll want to use an outer join to include all employees, and give different aliases to each instance of the employees table as specified in the from clause. Alright, let's now move to the second challenge. So for this challenge, you are to write a query to return all the products at each warehouse and include the following attributes: product ID, product name, warehouse ID, warehouse name, and quantity on hand. Alright, so coming up next are the hints. So you'll want to join multiple tables: the OES.products table, OES.warehouses, and OES.inventories. So you may find it helpful to check the entity relationship diagram of the sample DB database to see how these tables are related to each other. Another thing I should mention is that if a product is not at a warehouse, it doesn't need to be included in the query result. And likewise, if there's a warehouse which didn't have any products, that also does not need to be included in this query result. So you can use inner joins between the three tables. Alright, let's now move to the third challenge. So for the third challenge, you are to write a query to return the following attributes for all employees from Australia: employee ID, first name, last name, department name, job title, and state province. Coming up next are the hints. So for this challenge, you'll need to join multiple tables: employees, departments, jobs, and countries. And all these tables are in the HCM schema. Note that an outer join is required between the employees and the departments table. This is because you'll want to return all employees from Australia, regardless of whether they're from a department or not. Also, include a where clause to keep only employees from Australia. Alright, let's now move to the next challenge. So for the fourth challenge, you are to return the total quantity ordered of each product in each category. Do not include products which have never been ordered. Include the product name and category name in the query. Order the result by category name from A to Z. Then within each category name, order by product name from A to Z. Coming up next are the hints. So you'll need to join multiple tables, all in the OES schema. So products, order items, and product categories, and group by both product name and category name. Use the sum aggregate function in the select clause. Alright, let's now take a look at the fifth and final challenge. So this challenge is fairly similar to the previous one, in that you'll want to return the total quantity ordered of each product in each category. However, this time you'll need to include products which have never been ordered and give these ones a total quantity ordered of 0. Include the product name and the category name in the query. Order the results by category name from A to Z, and then within each category name, order by product name from A to Z. Coming up next are the hints for this one. So again, you'll need to join multiple tables: products, order items, and product categories. This query also requires an outer join. This is because now with this query, you're wanting to return all products, regardless of whether they exist in the order items table or not. Also group by both product name and category name. Use the sum aggregate function and nest the sum function within a coalesce function to replace nulls with zeros for those products that have never been ordered. Alright, so have a go at those 5 challenges, and in the next tutorial we'll be going through the solutions. Okay, welcome to the solutions to the advanced join challenges. So for the first challenge, you were to return employee details for all employees, and you were to include the first and last name of each employee's manager in the query result. So for the solution to this one, we are going to do a self join. So we are going to join the employees table to itself. So we have two instances of the employees table. Now, in the employees table, we have a one-to-many relationship between the employee ID and the manager ID. And this is enforced by a foreign key on the manager ID column, referencing back to the employee ID, but in the same table. So if we have a quick look at the entity relationship diagram, and if we look at employees, we can see we've got a primary key on employee ID, and it's a bit hard to see on this diagram, but we can see that it traces along here to where we've got manager ID foreign key. So this foreign key is referencing a column within the same table. So usually a foreign key references a primary key in another table, but in this case, this particular foreign key references a primary key of the same table. Okay, so if we go back to MySQL Workbench, so in our from clause, we have employees E, and then in this case, I'm aliasing the second instance of the employees table to the letter M, which is short for manager. We're doing a left outer join because we want to include all employees, even those ones that don't have a manager. So the CEO, they're not going to have a manager. So we're joining on the employee's manager equal to the manager's employee ID. Okay, so let's select that code and execute it. Okay, so we got 107 rows returned, and that's our total number of employees. And we can see that Jack Bernard does not have any manager, and that's because they're the CEO. And Don Riley, their manager, was employee ID 100. So this is Jack Bernard. So we can see Jack Bernard is here, and his employee ID is 100. So now we have some more information, not just the manager ID, but the actual manager first name and manager last name. And to explain further, in our select clause, we have aliased the first name column from the second instance of the employees table, which is M, and so we've aliased first name as manager first name, and we've aliased the last name column from the second instance of the employees table to manager last name. Alright, let's now move to the second challenge. So for this one, we were to get a couple of columns from the products table, which is the product ID, product name. We were to get a couple of columns from the warehouses table, so that's warehouse ID, the warehouse name, and we were also to get the quantity on hand from the inventories table. So let's first take a look at how these three tables are related to each other in the entity relationship diagram. Okay, so if we scroll down to the OES schema, we can see we have products here, warehouses, and inventories. And if we look at the inventories table, we can see that we have a composite primary key, and we also have two foreign keys on each column involved in the primary key. So inventories table is our association table, and it's called an association table because it's associating products with warehouses. So this foreign key here traces back to the primary key of the products table, which is product ID, and the other foreign key, the warehouse ID, traces back to the primary key of the warehouses table, which is warehouse ID. So the inventories table gives all the unique combinations of products at each warehouse. So what we're going to do is we're going to join the products table to the inventories table on the product ID, and then we're going to join the inventories table to the warehouses table on the warehouse ID. And along the way, we're going to be getting the columns that we need. So we're going to get product ID, product name from products, quantity on hand from inventories, and warehouse ID, warehouse name from the warehouses table. Okay, so let's go to MySQL Workbench again. And so here is the solution here. So if we have a look at the from clause first, we have from oes.products, aliasing this table to the letter P. we're doing an inner join, so we're inner joining to the inventories table. So we're only selecting products that actually exist in the inventories table, joining on the product ID in each of the two tables. Then we're inner joining onto warehouses, which I'm aliasing to the letter W, and we're joining the warehouses table to the inventories table, so inventories table alias to the letter I, and we're joining on the warehouse ID. And then we're selecting the columns that we need from each of the three tables. Okay, so let's highlight that and execute it. Okay, so we get 514 rows returned, and these are each of the products at each warehouse. So we can see for the Canon ink cartridge PG645, this is product ID 74, and it exists at warehouse ID 1, which is called the central warehouse, and we have 108 units of this product on hand. Alright, let's now move to the third challenge. Okay, so for this challenge, you were to return employee details and you were to include the department name and job title for all employees from Australia. So in the wording, we've got all employees. And so we want to return all employees, regardless of whether they belong to a department or not. So we're going to use a left outer join, and we're going to specify employees first. So it's on the left-hand side of our join. So we have from hcm.employees, aliasing to the letter E in this case, left outer join hcm.departments, aliasing to the letter D, and we're joining on the department ID column in each table. So we have e.department ID equals d.department ID. And as we've covered earlier, the outer keyword is optional, so we could have just written left join instead, and that would have done the same thing. But for now, I'm going to put it back in. Okay, so we join on the departments table so we can get the department name column, but we also had to get the job title column. And the job title column comes from the jobs table. So we're going to do a join to the jobs table. And in this case, I've used an inner join. So I've inner joined onto the jobs table. Now, you have to be a bit careful when combining inner joins with outer joins, because it is possible for an inner join to negate the effect of an outer join. In this case, it's okay to do, and to explain further, let's take a look again at the entity relationship diagram. Alright, so in our entity relationship diagram, we can see we've got a relationship between the jobs table and the employees table. So the jobs table primary key is job ID, and this relates to a foreign key in the employees table on the job ID column. So many employees might do the same job, but something that isn't shown in this diagram is that the foreign key in the employees table on the job ID column, this column here, job ID, is also not null. So this means that every employee is going to have a job ID value that is not null and that exists in the jobs table as given by the foreign key constraint. So to show this, if we go back to MySQL Workbench, so to see which columns have not null constraints on it, what we can do is we can go across to the employees table, right click on it, and then click on Table Inspector. So this opens up a new tab, and we can click on where it says columns, and if we look down here we can see job ID is int, and is it nullable, and we've got a no. So if it's a yes for the nullable, then this means that it allows nulls, and if it's a no for the nullable, it means that nulls are not allowed. So this has a not null constraint on it. Now the same isn't true for department ID. So if we look at department ID, it has a yes. So the department ID column does allow nulls, and that's why we needed to do an outer join when joining onto the departments table on the department ID, because even though it had a foreign key constraint on it, there could have still been some employees who had null for department ID. Okay, so let's close that. So that's the reason why we can do an inner join. So we're inner joining the jobs alias to J onto employees e.jobid equals j.jobid. Then we're doing again a similar thing, inner joining onto the countries table, which we're aliasing to C, on e.countryid equals c.countryid. So we don't actually need any attributes from the countries table, but if we look in the challenge, we wanted to get all employees from Australia. So we're wanting to join on the countries table so that we can use the country name column in the where clause as a filter. So we want to filter only those employees from Australia. So we have where c.countryname equals Australia. And the country ID attribute in the employees table also had a not null constraint on it, and hence why we can do an inner join. And if we have a look at the sample DB database, we can see that we've got the countries table has that primary key on the country ID column, and employees also has country ID, which is a foreign key referencing back to countries. Okay, so in logical query processing order, at a conceptual level, everything's going to get done in the from clause, then we apply the filter, then we do the select. So we're selecting the columns that we wanted. Alright, so let's highlight that and execute it. So let's just bring that up a bit, and this one as well. Okay, so we get 24 rows returned. So we have 24 employees from Australia, and we also have the job title for each of those employees. Okay, so if we bring that down a bit again. Okay, so before we move to the next challenge, I should mention that we could have written this one with left outer joins the whole way down. So we could have written it like this. So if we'd written it like this, we would have got the same result. Although just be aware that the first way of doing it was more efficient. So doing more left outer joins, the database has to do a bit more work. In this case, our tables are very small, so we don't notice any difference. But if we had tables with millions of rows in them, then doing inner joins is generally more efficient than doing outer joins. Okay, so let's now move to the next challenge. Okay, so for this challenge, you were to return the total quantity ordered of each product in each category, and you were to order the results first by category name from A to Z, and then by product name from A to Z. Okay, so when approaching a challenge like this, the first thing we want to do is to just join up all the tables that we need, and then we can calculate the total. So we want to get the total quantity ordered of each product in each category. So each product, so this indicates we want to use the products table in each category. So we want to get the product categories from the product categories table. But we also want to return the total quantity ordered of each product, and we can get the quantity ordered from the order items table. Okay, so let's have a look at how these tables relate to each other in the entity relationship diagram. Okay, so let's first have a look at the order items table. So the order items table is our association table, as it associates orders with products. We can tell it's the association table because it has a composite primary key, and we have a foreign key on each of the columns involved in the primary key. So we have a foreign key on the order ID column, which references back to the orders table, and we have a foreign key on the product ID column, referencing back to the products table. For this challenge, we don't need anything from the orders table, but we do need something from the order items table, which is the quantity. We want to also get the product names of each product, so we're going to be joining products to order items, and we also want to get the category of each product, so we're going to be joining on products to product categories, and we're going to be joining on the category ID column. So there's a one-to-many relationship between product categories and products. So one product category can have many products within that category. Alright, let's go back to MySQL Workbench. So in our from clause, we have from oes.products, we're joining. So in this case, doing an inner join. I could have specified the keyword inner, but it's optional. So in this case, I've left it out. So we have inner join order items, which I've aliased to OI, joining on the products.productID column equal to the order items.productID column. Then we join on the product categories table, which I've aliased to PC, and we're joining on the product categories category column equal to the products.category ID column. Okay, so we've joined up those tables that we need. Now it's time to do our calculation, which is the total quantity ordered of each product in each category. So where you see these words in each product and in each category, this indicates that we want to group by product and we want to group by category. So we'll do exactly that. So we're going to group by the category name, which is from the product categories table, comma, and then we group by the product name from the products table. And then in our select clause, we're going to include those columns included in the group by. So we have category name, product name, and then we're using the sum aggregate function, and we're summing up the quantity from the order items table within each of these groups. And I'm aliasing this to the column expression total quantity ordered. And finally, we're ordering by category name and product name from A to Z. So category name, first of all, gets ordered from A to Z in ascending order. Ascending order is the default, and hence why I didn't include the keyword ASC. And then within each category, we're ordering A to Z for product name. Okay, so there's quite a lot going on in there. Let's just highlight that and execute it. And if we bring this up a bit, so we can see in the cameras and drones category, we have a product name called the Andromeda drone with camera, and this has a total quantity ordered of 241 units. Okay, let's now move to the fifth challenge. Okay, so in this challenge, you were to return the total quantity ordered of each product in each category. So this is pretty similar to the last challenge, except this time you were to include products which have never been ordered. Set these to a total quantity ordered of 0, and then order the results, first by category name from A to Z, and then by product name from A to Z. So this is similar to the last query, however we're going to be including additional products which have never been ordered. So we want to have all products, even the ones that don't exist in the order items table. So we're going to use a left outer join. So this will return all products, even the ones that have never been ordered before. And for all the other joins, they're just the same as before. We can do a inner join here to product categories because we have a not null constraint on the category ID column in the products table. Okay. When we do this join between products and order items, the products that do not have an order item are going to have null for their quantity because of course they have never been ordered. And what we want to do is we want to replace these nulls with zeros. So as we have here in the challenge, it says set these to a total quantity ordered of 0. So to do that, we're going to use the coalesce function to replace those null quantities with a 0. So very similar to the previous challenge, except this time we're just doing a outer join between products and order items, and then we're using the coalesce function on the sum quantity. Okay, so let's just highlight that and execute it. And if we scroll down a bit, we can see that some of them are now 0. So previously we wouldn't have had this product, but now in this challenge we do have this product included. So we can see that the PBX 21-inch Series 9 monitor, it's in the PC peripherals category, but we've still managed to get it returned and we've given it a total quantity ordered of 0. And if we go down to the output, we can see that now we've got 79 rows returned, whereas for the previous challenge we had 77 rows returned. So we can see that we've got 2 extra products that have never been ordered, and we've included them in this final challenge here. Okay, so some of these challenges you might have found pretty hard. You might want to go back and review some of the earlier lectures, as it takes a bit of time to learn how to do these advanced joins. Alright, so that's it for this lecture. See you in the next one.